Okay. So you have to find a way to get some more information from bright field microscopy images. And there so we have to figure out is it possible to predict fluorescence images from bright field cell images? And I think the deep learning model is an approach with a conditional generative adversarial network, so CGAN for short. And why this might work? So the CGAN learns a mapping from input image A to output image B. So basically, this should be your output. This is the ground truth. And um, there are two neural networks in CGAN, a generator and a discriminator. So the generator tries to fool discriminator into seeing the fake, the fake output is real. And the discriminator tries to tell between the real and fake. So it is possible to synthesizing photos from labeled maps. For example, this is the best example I can find, actually, and even transforming sketches into photos. Since both bright field and fluorescence images capture the same thing, basically the same cells and structures, the statistical correlation exists. Now let's talk about my data set. So the original images are kind of big, is 2048 pixels times 2048 pixels. And I have to downscale them to 256 to 2. So basically, I have to reduce the resolution by a lot uh, due to my hardware constraints, you know. And so basically, the images here are my image set. So the left here are the bright field images, and right here are the fluorescence images, and they are both in grayscale. So the total amount of image set in my data set is 1986. That's not a lot, to be honest, but that's the data set I can find. Let's
Can
go
I
over.
can I ask a quick question? You
uh,
said you reduced the resolution from 2048 to 256.
uh-huh.
Is that truly the resolution was reduced, or was the field of view reduced?
It's the resolution because in my Python script, it reduces the resolution.
And you chose to reduce the resolution versus just a smaller field of view because why?
Um, um, because I think like either will work, but I'd like to preserve like more cells to show maybe that will bring a better result. But yeah, I think either will work. Yeah.
Okay.
Okay. So let's go over some basic concepts. The first is convolution. So basically, it extracts features like shapes, outlines while reducing the noise. This is a basic illustration of how convolution works. So basically, for this pixel, um, we use a filter, like for example, 1 times 1.2, and added all of this together, we get a number. So this is a convolution, the result of convolution. And a rectified linear unit, or ReLU, uh, it lets the network learn relationships like curves, textures, edges, and other nonlinear structures. So it often applies after the convolution. So both convolution and ReLU are used to extract the features. And there's also max pooling. So it takes a region like 2.2 and keeps only the maximum value. So this is a way to reduce the spatial size. It's also called downsampling and keep most important features here. Okay, now let's talk about the generator. So the generator is basically a modified UNet. First, what is UNet? So it generates real-looking images in the CGAN. And in the UNet, there is a part called encoder, and there's a part called decoder. So basically, this contracting path is encoder, and this is decoder. The encoder compresses the input For example, input is 572 by 772, and into abstract features via convolution. So these are the convolution. This blue arrows are convolution, and max pooling. Sorry. So it learns what is in the image by generating feature maps. So this number here are the number of feature maps in each level of this convolution at max pooling. And these feature maps are basically like the image that shows where and how strongly a certain pattern appears in the input image. And the decoder reconstructs a new image from those features by reverse process encoder. So basically, the decoder is just a reverse process of the decoder. Oh, well, no. The decoder is the reverse process of the encoder. I'm sorry. Okay. And the resolution of image decreased several times. As you can see here, this is 570, 568. This is like 280. This is like 140, 68, 64, 32. So the resolution of image decreases several times in the contracting path. Does that mean the final detail of the image is not? Actually, the detail is not losing here because of these gray arrows. They are called like the copy and crop. It connects encoder features to decoder layers here at the same resolution. It helps decoder localize objects accurately and prevent loss of fine detail during the downsampling. So the last word about generator is it learns when I see this kind of pattern, I should paint this kind of output. Okay. So this is the generator used in this project. So basically, it's from like 256 to 256 to 4x4 is can I like make it larger? Yeah, with 1024 feature maps. And the strided convolutions are hidden in these sequential blocks. Um, so the strided convolution is basically just like I mentioned earlier. So this is convolution. We go by this pixel and that pixel. Strided convolution is like we do one pixel and skip several other pixels and do the next pixel. So this is also a way to reduce the resolution of the image. Okay. And so the input is the bright field image and the output is the generated fluorescence image. And the generated output goes to the discriminator. Uh, how many how much time did I pass?
That was 9 minutes, so you have about 11 more minutes.
Yeah, I think that's enough. Okay. So this is my discriminator. So basically it takes the fluorescence image and the bright field image. This is so input here is the bright field image. The target image is the fluorescence image, and they combine all layers together. So basically by this concatenate step. So similar to UNet, it uses strided convolution to reduce the resolution and extract the features. And in some steps, zero padding is also involved. So basically, it adds edges of zeros around the border of the input. For example, if this is an image, we add a round of zero. And it prevents the image shrinking because if we don't add that round of zero, uh, some uh, some pixels around the edge might be unable for convolution. The output here is a 30 by 30 by 1 matrix with numbers between 0 and 1. So it gives a realism score at like each pixel of the output. So every of these 900 numbers will be used to calculate the sigmoid cross entropy. We will talk about it in next slide. So here's another round of concepts. I guess they are not no longer basic concepts. They are very confusing concepts. So first, what is mean absolute error or MAE? It measures how different two images are pixel by pixel. This is the function. And the sigmoid cross entropy. It measures the difference between the model's prediction and the correct answer. This leads to the adversarial loss. So this is a loss function, and this is the function for the sigma cross entropy loss. And there's also a parameter called lambda. So this is the weighting factor used to balance two losses in the generator. For example, the total loss is defined by this adversarial loss and lambda times MAE. The high lambda means better to better pixel accuracy, but maybe in the sacrifice of the realism. And the low lambda means the realism is more important here. Um, and apply gradients. This is the most confusing concepts. Actually, I'm still cannot totally understand this. So this step compute error and update the filters to improve the result. The filters is just in case you are wondering, the filter is just this thing. Sometimes I also call it kernel, but it's just the same thing. You can understand. And so how do we train the generator? So the generated image is used to calculate the MAE from the real image and will be put into the discriminator. The discriminator will produce realism scores while we pretend all generated images are real. So when the realism score is closer to one, the adversarial loss from the sigmoid cross entropy is little. So that combines with the lambda times MAE, as I mentioned earlier, we get the total loss. We can use this data to apply the gradients. And the goal here is to fool the discriminator. So the discriminator think all of your generated stuffs are real. So we have to keep the total loss real, low. So, okay. How are we training the discriminator? So discriminator takes a bright field image and corresponding fluorescence image, either the real one or the generated one. If the fluorescence image is the ground truth, 1 will be used to calculate the adversarial loss. And if the fluorescence image is generated, 0 will be used to calculate the loss. The losses are added together to apply the gradients and feedback to the discriminator. The goal here is to push the real predictions towards 1 and the fake predictions towards 0. And before I show you the training result, so this is basically my training setup. I'm using my own gaming laptop with Java 3.0, and I'm running TensorFlow 2.0 because this is the last version that has the GPU support on Windows. I tried to install Linux on Windows, but I couldn't figure out how. So I can only use this a little bit like old TensorFlow version. I think this was released like back in 2023, so it's not that old, I think. Yeah, and so TensorFlow is a framework to construct all of this kind of neural networks. And it also includes an important function called TensorBoard. So it tracks the training progress, the loss versus minutes. So here in this image, this is the time in minutes. After each 100 minutes, it goes back to the 0. So that's why you see this like horizontal lines. And the vertical axis is Gen L1 loss. So basically, in the code, this is MAE. And here are some results. I'm not sure if you guys can see it clearly, but you guys might have to like increase the brightness of the screen because there are some uh they are kind of dark here. So ground truth, this is the ground truth, this is the predicted image. And I'm gonna be honest, these are the best ones. Yeah, they are worst ones. Okay. So the MAE might be increasing over time, not decreasing. So that's because uh you guys can see this, right? So the
Huh?
MAE actually might increase over time. Yeah, it's not always decreasing. That's because the generator and the discriminator, they don't have the same training speed. So to make this training more efficient, we have to tune the training plan. So basically the batch size, the lambda, or maybe even the data set. And there seems to be a limit where the MAE cannot be lower. And MAE cannot be zero, that's for sure. Because after all, this is a predicted image, not the ground truth. And
Is it possible for you to select one of those or three of those images and change the contrast so that we can see something? Because to be perfectly honest, the first column is mid-gray, the second column is dark gray, and the third
um,
column is slightly brighter gray, but there's no features in the pictures on my screen. So I can't really.
there are like some features I'd say you can see, for example, here. But I have to like maybe put these images into like Photoshop, GIMP, or some
Yeah. Well,
image
if you
processing
click on it
algorithms.
with your mouse, click on that picture with your mouse. Is it an individual picture? Okay, so you got three
Um,
there. There should be a way to change the contrast. Uh,
uh, this is the output in my Python notebook. So I just take the screenshot of them.
I see. I see.
Yeah, but if you really want, I can show you the Python the complete code. Yeah, actually I can do that. But
Well,
uh,
I don't care to see the code so much as see images that have features in them. Because I don't really see anything in these pictures. Oh, I see there's some very dim things in the second row there. Okay. And so what's the difference between all these rows and everything? What is this?
so this is the bright field image, this is the ground truth, and this is the predicted image.
Oh, and these are just different examples as we go from top to bottom. Is that what you're showing?
Yeah, these are the different examples. These are
I
the
see.
best result I can find, to be honest.
I see.
Yeah, let's to show the training effect.
Uh,
Okay.
and it says here lambda is 1,000. That's a big number.
Yep.
What is the range that lambda can achieve? Like if I set it to one, uh, what is the balance between the two uh,
Um,
numbers?
I chose 1000 because I tried other numbers, but 1000 seems to be the one with the lowest MAE I can get. I mean, in a reasonable time. For
And so when you
example,
set it to 1,000, does that basically eliminate one error testing part and put everything into the term that has the lambda 1,000?
um, well, that's a good question actually. And but
Like if I go to that
um,
formula and I look at my total loss, and you have adversarial loss and you have lambda MAE, and I set lambda to 1,000. I don't know the range of adversarial loss in MAE. Is it 0 to 1 or is it?
MAE mean so
So we don't basically know what 1,000 means in this formula in terms of balancing the MAE and adversarial loss.
yeah, to be honest, I read some papers and other people's article. This all they sometimes start with like 100.
Uh-huh.
Yeah, but I tried 100, but the result is like worse compared to 1000.
I
So
see.
yeah, I use 1000 at last.
So there wasn't really any tuning of lambda as such. You just a big number seemed to work better.
Um, So maybe I should try more lambda values to be honest, but this is the best one I can find.
Okay, it seems oddly specific that it came out to 1,000. But anyway, I don't know
Mhm.
what the dependence of the performance versus lambda and anything like that. We'd have to know, right? So,
Yeah.
okay, all right.
Okay. So some summary and reflections. So the project explores the possibility of translating bright field images into fluorescence images, and this might be a helpful technique to image living cells. And the concepts involved in artificial neural networks are investigated, bringing an introductory level understanding of CGAN. And a CGAN was built, including a generator and discriminator. The training result can be observed via a quantitative way. So basically, we can track the L1 loss here. And the detailed math behind these concepts are not thoroughly understood, especially for the applying gradient part. Actually, it took me some time to even understand what even is a gradient. And maybe I can try this network on other image translations, for example, DLC to fluorescence, or maybe like from fluorescence to bright field, like translating back. I might also use larger images for training, start with 512 by 512. And here are my references, and that's all. Yeah.
Okay, thanks. So the one big question obviously is why do you pursue the hypothesis that you can generate a fluorescence image from a bright field image? What physical underpinnings of bright field microscopy directly map to fluorescence? So that you
Um,
know that if I have the bright field, I know kind of how the fluorescence will look. There's enough features in here that tell me what the fluorescence is probably going to look like.
so as I said in this page, they are essentially the same structure. So there have to be some statistical links. And yeah, I just read about this idea and I feel like because of statistical links exist, this might work. Yeah.
Okay.
Mhm.
I
Any other questions?
Does anyone from the class have a question for
I have a
Jason?
Okay.
question.
Hello, Cassie.
Um,
Cassie?
I thought your results looked really good. Like we're doing again and we're struggling a lot. So I'm impressed that it looked like to me your ground truth looked exactly like your the output. Um, so I don't know. I'm just curious, like if you didn't change the lambda and like the weights in that way. Like I'm just curious what you changed in order to get a good result, basically.
Yeah, so lambda is of course changed a lot here. But I also changed the depth of the generator. So the the depth here, so this is 4 by 4. It can even be 2 by 2 or 8 by 8. They will also change the result. And well, to be honest, these are the best result I can get
Hmm,
to show here. They are worst results, so don't worry if you are doing the same thing. Okay. Yeah.
cool.
Okay, great.
So hi. This is the project done by my partner Bryce and I, and our project will discuss deep learning-based dual phase segmentation of the left atrium and left ventricle across cardiac phases. So just to give a quick overview of what cardiac segmentation is, it is defined as a process of identifying and outlining specific anatomical structures of the heart. It is essential for assessing structural and functional cardiac health, and it can produce measurements as its outputs, such as chamber volumes and ejection fraction. It can help with a number of conditions, cardiac conditions, such as heart failure, myocardial wall thickness, and ejection fraction. So there is manual segmentation that has been done in the past before, but more recently with with the revolution of AI and deep learning models, there's the introduction of unit, as mentioned in the previous presentation. It can be defined as a convolutional neural network or a CNN, and it automatically segments 3D structures, and it can provide accurate, reproducible, and fast annotations to support diagnostics and surgical planning. Um, so the input for this model, for these models, are 3D image volumes, and for the outputs, they output 3D segmentation masks. So what are segmentation masks? So if you look on the image to the left, this is an example picture of an elephant. So let's say you only want the output of the segmentation mask output to only feature the elephant. So so what masks do, there are different type of masks. There are binary masks, which is an example of the elephant here, where you want where zeros can where the model applies zeros for background voxels and ones for whatever the region of interest is. So in this case, it would be the elephant. So the the model would apply ones and color the region of the elephant green, and that would be the mask. And the output or the segmented image would be the mask and the original image laid on top of one another. So you can see that the mask clearly outlines the elephant and the outputted segmented image. So to go more into our motivation slash problem, so as previously mentioned, manual segmentation has limitations. There's significant human labor as each scan can take up to 30 minutes. And there's also variability into cardiac assessments where different cardiologists can interpret these images differently, which can lead to um, conflicting results. So automation is needed to improve the scalability and standardization. Chamber compliance and systolic performance need observations of end diastole and end systole phases. So with our project, we aim to reduce time and variability between observers, enable segmentation of both left atrium and left ventricle, use end diastole and end systole images to improve diagnostic accuracy, and calculate the stroke volume and ejection fraction. So as I mentioned, there has been advances in 3D deep learning models using UNet, um, but we found based on the current state of the art that current models are limited to either the left ventricle slash the left atrium, or conversely, one of end diastole or end systole. Um, so more to get into the problem or the clinical relevance of how our project would fit into the to I guess the medical imaging field, it will be able to accurately um, quantify ejection fraction and stroke volume estimation. It can also help with diagnosis and risk stratification for heart failure and atrial fibrillation. It can also reduce the manual workload for radiologists and cardiologists as they can just feed it into the deep learning model and gain outputs relatively quickly compared to manual segmentation. As I mentioned before, another big problem was the variability between the cardiologists and their assessments. So this would help standardize measurements across not only cardiologists working in the same lab, but also across different institutions and observers across multiple locations. It could also help facilitate early detection of cardiac remodeling and dysfunction. And it could also hopefully seamlessly integrate itself into clinical workflows that already exist, such as PACS, 3D Slicer, and ITK Snap. So our objective, or I guess our problem statement, is we aim to develop a deep learning pipeline that employs dual phase segmentation of the left ventricle and left atrium from 3D cardiac images at two key cardiac phases, which is the end diastole and end systole. So now we'll talk more about our data set. So our data set, we're from 40 subjects, each with 3D volumetric images at end diastole and end systole phases, which results in a total of 80 images. So as we talked before, each image came with their individual mass for both the left ventricle and the left atrium, and no left ventricle and no left atrium labeling or the mass overlapped. Um, Ground truth labels were done to show exactly where the left ventricle and left atrium were located. And then this is the images. Uh, I guess, and cyan, the cyan color is labeling the left ventricle, and the blue with the more darker blue color is where the left atrium um, would be shown over time in the scans. Yeah. So next, you can go into more of our pre-processing. So before we fed the data into our model, we wanted to make sure that it was very consistent and very there were no outliers, and we wanted to make our model as precise as possible. So during inference, you feed full images with air too, just as real world images account have not only have the cardiac system, but also have background artifacts such as air or other things. So we tried to replicate this as accurately as possible, and we manually removed files with depths unequal to 256. So as we see on the graph here, um, a large majority of our images had an image depth exactly to 256, but we found that some images had there were outlier images that had depths such as maybe like 120 or like 410 or like 650. So we decided to remove those images as we wanted to make our data set as consistent as possible. And we also chose to resize our images from its original size of 512 to 512 by 256 to 128 by 128 by 64 to to make the training segments of our model more efficient. Uh, in addition, there's additional pre-processing as well. So uh,
Can
we
I
normalize,
ask a quick question about that? Can you
yeah.
define what depth is? I'm not sure I understand.
Depth is the z-axis of our images.
Oh, number of slices?
Yes.
I see. Okay. And so you basically unified everything such that it went into this 128, 128, 64 over the whole original field of view?
Yeah.
Okay. So you didn't isolate the heart, you just did the whole thing.
Yeah. Yeah.
Okay.
Uh,
Were the Okay, and so the 128 by 128 by 64, the actual spatial dimensions of those voxels varied from person to person.
yeah.
If they were in millimeters, they would vary because it's
Yes.
okay. All right,
Yes.
thank you.
So also we decided to normalize the intensities as we found that a lot of the current models normalize them as well as we looked through papers and such. So we decided to use min-max values. There are other papers that um, normalize using z-score values, but we found that min-max values were better for our model, and we decided to put these at 2,000 Hounsfield units and then at a minimum of a negative 2,000 Hounsfield units. And we did this in order to account for scanner variations across institutions and as well as across different images as well. And for specific augmentation, we chose to account for breathing corrections and movement during the CT scans. So we found that rotations were the best augmentation in order to replicate this. So in order to try and show the movement or breathing corrections during these scans, we decided to incorporate random rotations of plus or minus 5 degrees in order to show this.
About
And
what
also,
axis are you rotating? I'm sorry.
we're rotating around the all three axes, so X, Y, and Z.
Oh, I
Oh,
see.
we're just doing along the XY plane. So along the axis.
I see. So you have an XY image, Z is perpendicular to us, and you rotate this way.
Yeah.
Yeah.
Okay.
And we also did some class balancing to add weights to address tissue volume imbalances from image to image. Um, so yeah, so that was our pre-processing, and now Bryce will get into the nitty-gritty of our training and results.
All right. Um, hi. So I'll talk about the model architecture. So this is the UNet that we're using. So it's pretty lightweight. Also, like, I think Jason talked about it a little. And So we're employed a 3D unit. So I think he's using the 2D one. So to change it to 3D, we're basically um from the just make the functions inside the inside the 2D unit, just make it 3D, and that way we'll preserve the through plane anatomical continuity. And the architecture uses a classic encoder-decoder structure with 5 downsampling layers, and this increased the filters from 64 to 512, and this capturing the features at multiple scales. And we use 5 upsampling layers, include dropout for regularization and reconstruct the full resolution segmentation. A key feature of our model is the incorporation of dual phase ED and ES volumes. And I want to clarify that we actually trained separate models for different phase combinations data to compare their effectiveness, and that's our method to incorporate this. And and we use skip connections for spatial detail preservation, and um and the outputs is multi-class, so background, left atrium, and left ventricle.
Can I ask a quick question? When you say mul you had two networks, one for end diastole and one for end systole?
Oh, we have actually three. So like in diastole and in systole, and then we pulling all the data together and separate them 50-50, and then train another
Oh,
network
so you
to
have
see like the
one network that did end diastole, one that did end systole, and one that worked on shuffled data that has
yeah.
both phases. Okay.
Um so to our training procedure. Our training procedure was designed to handle the computational constraints. So we resize it, and then we address the class imbalance, and we use 50-50 ratio to make the three models consistent. And then we have tw 20 epochs, and using batch size 2. And for the loss function, we use the TensorFlow default sparse categorical cross entropy loss. And and this is because shown in the figure below, you can see the segmentation inside the whole thing is pretty small. So I think this loss will entail that. And the and we use dual phase versus single phase. And here's the dual phase results. So this approach we trained on both the NDAS and systole data combined, and the training curve shows excellent performance. We achieved rapid convergence with validation accuracy reaching approximately 97% and maintaining stability throughout the training. And the loss curves showed the model learned effectively without overfitting. With training and validation loss both decreasing steadily. And I think what's particularly interesting is how the model quickly converged. So on like epoch 2 to 3, we're already achieving some of the very good results. Um,
How do you explain the training accurate or the validation accuracy being so high on your first epic?
um, okay, so I th yesterday I think about it because I think it's weird. I think my explanation is like, so the data looks re like fairly alike. So even if you're just seeing like a couple training data, I think that's enough. I don't know, like I think I still need to like work on it, but that's my hypothesis is like those like 3D images, they look basically like structurally alike, and then I think that kind of explains why the accurate and I'll show in the single phase the accuracy is pretty high as well. So I think that might be one reason why. But
It
The
does
loss
feel,
value also looks pretty low if you like it's not starting from a very high loss and then
yeah, exactly.
like trading for a loss thing.
I see. So that loss that is very low to begin with, so it just
Yeah.
maps to that accuracy. So accuracy is not a sort of sensitive marker.
Yeah, I think it's maybe also like changing the loss function may change like the how the model learns
So
as well.
I see. But does this have anything to do with the fact that you're using the whole volume and a much smaller heart in that whole volume? So calling everything zero, your accuracy is going to be pretty high. Right.
Oh, I think I think we're capturing the whole image.
Yeah.
If
But this goes back to that
yeah.
balance, right? You've got a small heart inside a big volume, relatively speaking. So even if your network just said none of this is hard, the accuracy would still be pretty good because it would get so many right.
That's true, I think. Hmm. Yeah, I think that's
How
true.
big is your data set?
It's only like 80 data,
Yeah, I
80
think it might be just
plus.
memorizing everything.
Oh, okay.
Yeah. All right. Going to the next. But this is just a visualization of our predicted mask, and I think it did a pretty good job at like this specific one. Not like I just looked at a couple and they did pretty good. Um, so you can
What,
see.
I'm sorry, what am I supposed to compare? Can you take your mouse and tell me what I should be comparing here?
So the above is like the true mask.
Yeah.
So basically, we're taking the 26 slice through 43, so like 18 slices.
Okay.
And we want to see the segmentation in each slice. So
Okay.
comparing like up and down,
Yeah. Okay. So
you
I
can,
see it's very good in the middle row and the bottom row. There's a bit of problem in the middle row, I guess, on 33 is a little bit different. And 34 is quite different, and 35.
yeah.
Yeah, okay. And then 26 seems to be, it's gone crazy,
Okay.
right?
Um, so that's some like minor visualization issue or like plotting issue that I have. So I forgot to like say like, okay, so label one is one color and label two is one color. So when the picture has only like one label, so for example, like left ventricle, so it just assigned one, like the
I see.
default color.
I
So
see. It's a
that,
bug when you only have one label. Okay. All
yeah,
right.
yeah.
Yeah, got it.
So I think it kind of captured the structure pretty well.
Yeah, yeah, it's not bad. I mean,
Yeah, also I think the the imbalance should is also a big issue, I think. Because I think I tried like different weights. I try so instead of 1 2 2, I try 1 3 3, and then the accuracy is pretty high, but when I look at the visualization, I didn't I think they're all like zero. So that might explain why
so
like if you
these field of views that you're displaying here, that's the original field of view in the image that you were using?
yeah.
Okay. So the heart is a significant part of that field of view, right? I mean, it's still the ventricle is still probably a, I don't know, a tenth or something, but it's not 1% or something.
Yeah, it's not. It's the whole image. Okay.
Okay.
And here's the
Go,
res
go ahead.
yeah. Here's results just trained on the and diastole data, and it just follows the same trend, and accuracy is really high just from the first epoch. Um
Mhm.
and still like the loss is like low in the beginning. Um, I think we can just jump to the visualization. So here you can see they also did a pretty good job. So this is like tested on the end systole data. So we train on the endasily data and then we validate them in systole data, and it did a pretty good job at
Mhm.
identifying everything. Yeah. And the same trained on the and systole data and visualization is pretty good. So to our discussion. So the key finding to me is surprising is that even though we train on only single phase, it can generalize across cardiac phases. And since we're only used this very lightweight 3D unit model and it learns the anatomy features fairly quickly, it 20 we only take like 2 minutes, and it is really high accuracy. Maybe suggest like effective pre-processing, but also suggest some like error about the class imbalance. And clinical implication, this could potentially be used for automated cardiac assessment and reduce the radiologist workload and standardize the measurements across institutions. Here's some limitations. So first, the data set size is pretty low. We only have 40 patients versus thousands needed for clinical validation. And also, this I forgot to ask about the pathology diversity, but I assume it's not that diverse. So, need validation across cardiovascular disease spectrum. And we also only did like rotation across the axis, and it's limited to 5 degrees. So remotion can be more severe and more like complicated. So, and also we can evaluate more weights, and future iterations could implement like automated hyperparameter search.
I'm sorry, what do the weights correspond to? I missed that. Must have.
Oh, so the weights, so we basically assign, um, so basically 1 to 2 is one. So the first element is background, and then second, third is left atrium and left ventricle.
Uh-huh.
So basically, I assign like more weights to the atrium and left ventricle to kind of mitigate the imbalance of the
I see.
classes.
Got it.
Yeah.
Okay, thank you.
And but surprisingly, 1 to 2 works better than, so 1 to 2 is what I've shown, but 1 through 3 just totally like zero, like background, but accuracy is pretty high as well. So that makes me wonder why.
I'm sorry, 133 did what? Different than 122?
The 1 through 3, when you visualize the data, the segmentation, it just assign everything to background, but the
Oh,
accuracy is still pretty high.
I see. Okay.
So yeah, so maybe that's a problem.
Yeah.
But surprisingly, 1 to 2 works pretty well. So
Okay. Cool.
maybe we're just lucky. Yeah. All right. So conclusion, um, and future work. Future work, we could use different augmentation, like I said, because the movement is pretty complicated. To use like rotation across different axes and then combining like translation, shearing, and like them together to monitor it. And then we could include other parts of the heart, and we could integrate with workflows for easier access.
Cool.
That's our references.
All right.
Thank you.
It's hard to know unless you had people that actually do have that disease where your body is reflected through the midline. Like some people have mirror image bodies, uh, but reflections
Yeah.
otherwise, I'm not sure unless somebody fed the data in the wrong way. But okay, that's kind of supports, our observations that a lot of these networks can get trained very quickly and on very few examples if you have data from the same place. Like if it's from the same scanner and the same protocol, we've also found that you can train a network in like tens to dozens of images, and it'll do pretty darn well on the 10,000 images that are left out. So which is good, right? So this sort of confirms that hypothesis to a certain extent. Cool. Any
Yeah.
questions from the class? And and if I understood correctly, you said your network trained up in 2 minutes?
Yeah. We only use like 20 repetition.
Wow.
So yeah, it's just amazing how this very lightweight model
Yeah.
can, yeah, I don't know, just AI, I guess.
Yeah, that's amazing. Um, okay. Yes, sir. I can see it.
Okay, great. Let me start my timer real quick. All right, hi everyone. Today I'll be presenting my project, which I pitched 3 weeks ago. I titled it Incorporating Left Atrial Global Metrics to Left Ventricular Strain to Predict Response to Cardiac Resynchronization Therapy, or CRT. Okay, quick 30-second overview of the clinical need area. CRT is a well-established treatment for patients with heart failure, but approximately 30% of patients do not respond to the therapy. Although it's not open heart surgery, it's still invasive under anesthesia and should be prevented if not necessary. Therefore, it would be advantageous if we can use tools to better inform patient response. While echo and MRI have been used to improve lead placement, their limited reproducibility and their compatibility have prevented adoption. So here we'll explore the use of 4D-CT to better predict response to CRT. So this is a slide I presented last time. It's going through the study of Ashish and Dr. McVeigh back in 2023. To summarize just real quick, 82 patients were retrospectively analyzed. They received the 4D-CT scans before and 6 months after CRT. The team had manually segmented the left ventricle across all the time points for each of the patients, and using this mask, they could then calculate where's my mouse here? The global and regional strain metrics and append them to each patient's clinical features. By moving to the last box, they then trained a support vector machine to generate an overall score per patient, and by assigning a threshold value, patients above this value were predicted to respond to the CRT, and below this value, they would not respond. The overall conclusion was that both the global and regional strain metrics of the left ventricle could be used to predict CRT response. And with this model, they achieved AUC or area under the curve of 87%. I added the slightest feedback from Dr. McVeigh last time, but ultimately, why do we care about the left atrium? So in left-sided heart failure, the left ventricle struggles to pump blood, which can cause pressure to back up into the left atrium, and over time, this can lead to left atrial enlargement and potential damage. It can go through structural changes like hypertrophy, lose its ability to act as an effective pump, and even contribute to mitral valve issues. So given all that, we're asking, can these measurable changes in LA function, or specifically LA strain, help us better predict who will respond to CRT? This is the proposed plan slide I presented last time, and in the flowchart, I highlighted the adaptations to Ashish's methodology in blue, while the gray boxes are what stayed the same. And this is what I was able to get done. So the checks are what I was able to get done, while the crossouts I either didn't get to or we decided to move in another direction. So to start off, I used the same 82 patients with pre and post TRT 4D-CT scans. We didn't get the chance to test on more patients, but this could be a potential next step. Then I was able to use a segmentation model to segment 9 chambers of the left heart for all patients across all time points. So this includes the left ventricle and the left atrium. And moving to the middle, for the metrics, after computing and analyzing with left atrium global values, the results looked pretty decent. So we didn't or I didn't feel the need to incorporate the regional metrics. And then lastly, for the models, I was able to replicate Ashish's findings with the SVM, as well as input the features table into two additional supervised learning techniques, including the random forest and a logic gradient boosted tree, which is pretty similar to the XG boost, but that's the only one that was available in MATLAB. And again, the results look pretty good with these models, so I didn't go forward with the deep learning with the CNN RNN hybrid model. And before I go over the AUCs, I'll explain my methodology in a bit more detail, just in case y'all have any questions. But my first step was segmenting using the segmentation model. So with the help of one of my lab mates, Amanda Crane, we were able to adapt this heart segmentation model that was developed by Lauren Severance, one of Dr. McVeigh's former PhD students. I used it to segment 9 chambers of the left heart across all time points pre and post CRT for all 82 patients. So that's a lot of data. First, I was running CPU and it took almost a week to run, but then I did a GPU and it was less than a day. So that was pretty cool. Individuals, the red corresponds to the left ventricle and the green corresponds to the left atrium. So you can see here the 3D rendering of one of the time points. Again, the red, the largest is the left ventricle, and the green is the left atrium. And yeah, pretty good results. And first, I just want to review the features table and what it is. So these are the contents of the original features table that Ashish used back in 2023. The table includes clinical features as well as left ventricle, regional, and global metrics. But what's important is that these strain values were calculated from segmentations that were drawn manually. So that differs from my model because in my updated features table, we have the clinical features as well as the left ventricle, global, and regional strain metrics, but these metrics were calculated from the segmentations that were automated, like I just said, from Lauren's model. So we have both manually as well as automatically derived global strain metrics for the left ventricle. The major change is the addition of the left atrium global strain metrics, obviously. These included the maximum and minimum volumes across the time series, almost as proxies for end diastolic volume and end diastolic volume for the left ventricle. I also included the left atrium ejection fraction from these values and then the sphericity. So to calculate the sphericity, I divided the actual volume of the left atrium by its theoretical volume had it been a perfect sphere, which is calculated as pi over 6 times its longest axis cubed. Okay, so some sanity checks just to make sure that our segmentation worked. The segmentation was actually my biggest bottleneck. So there were many, many different redos because there were many repos and I had a bunch of compatibility issues, but eventually we got there. So pretty happy that we got there. So instead of looking at every patient's before and after scan for all 20 time points, Dr. McVeigh gave me the idea to plot everything and inspect for any outliers. So here I did just that. Here, I'm looking at the left ventricle's ejection fraction from the manually versus automatically derived segmentations. The graph you're seeing is plotting all of the patient IDs on the x-axis and the ejection fraction percentage on the y-axis. For each patient, we are only plotting the ejection fractions from the pre-scan, from the pre-CRT scan, since that's the only manually acquired segmentation that we have. The X corresponds to the manual acquisition and the filled in circle to the automatic. If the difference between the two is larger than 10%, it should have outputted as yellow. And as you can maybe see in this graph, there's no yellow, which means the model closely mimicked the values of the hand-derived segmentations, or at least the difference between end systolic volume and diastolic volume was consistent between the automatic and manual methodology. So that's pretty good news. Defining response to CRT as a decrease of 15% or greater of end systolic volume from before to after treatment, we defined 53 patients as responders and 19 patients as non-responders using the automated segments. So this is really close. This corresponds to green and red on the x-axis, so green responder, red non-responder. This suggests that one patient may have been right on the cusp of 15%, resulting in a different label between automated and manual. So all in all, I was pretty satisfied with the segmentation performance without having to load every single patient and time point into ITK Snap. But again, we could do that just to confirm that the absolute values are correct. So then, just to ease my worries, I plotted the left ventricle volumes over time. Um, so in the plots, time point is on the x-axis and volume is on the y. As you can see, there are no massive outliers, and most patients follow the inverted bell curve trend, in which the outlier points are the maxes and the center point is the min, or like near the center. We can therefore define the first time frame as end diastolic volume and the minimum volume time frame as end systolic volume for left ventricle. So, lastly, the volume magnitudes do make sense, and therefore I can pretty much suggest we trust this data. We believe this data. My next sanity check, I was going to do the exact same thing, only now for left atrium. So recall that the left atrium fills with blood during systole while the left ventricle is draining blood. Then when the left ventricle is filling with blood during diastole, the left atrium is draining blood. Thus, we expect the graphs to have the opposite trend and be right side up bell curves, which is exactly what we see. Although not as clean, we still see the same general trends for all the patients. I inspected one of the outlier points, like the top patient over here, just to see what was going on over the time series. But the segmentation looked pretty good on ITK Snap, so I kept them in the final model, but we can always take them out if necessary. Also, because the left atrium is smaller, the volume magnitudes do make sense, and therefore I think I pretty much believe this data without having to look at every single segmentation.
That
Okay.
also, can we pause for a second on that? That is the first time I've seen this data. It's really cool. So left is pre, right is post. Is the y-axis the same between left and right? So the shift in the data is an actual shift?
Correct.
Okay. Yeah, that's pretty impressive, right? How responders are going to be these people whose LAs have shrunk, right? Because
Yeah, what I could have done is like color code them responder, not responder, but MATLAB bugged out after 50 legend entries. So I couldn't even clear off. Yeah, I mean, I could have plotted them on two different or on four plots instead of two,
yeah,
but yeah, they're showing absolute differences.
no, that's pretty cool. Yeah.
All right, so before diving into the model results, I'll quickly review the learning models I tested in parallel. Um, I don't want to get too much into the weeds, but I think it's we have to understand some of the nuances between them and why some of them may perform differently. So first of all, they're all supervised learning techniques. So support vector machines or SVMs are about finding a hyperplane that separates two groups, which for us are the responders and the non-responders. They can handle different shapes in the data with kernels, and they're usually pretty stable, especially when the data set is a bit noisy or when we don't have tons of features. They're also less likely to overfit compared to the other models. That's important. Random forests are essentially a team of decision trees. Each tree looks at a different part of the data, and they all vote on the final result, essentially. Because of this randomness and teamwork, they're good at avoiding overfitting and can pick up on complex relationships in the data, especially when things aren't purely linear. And then we have the or the logic gradient boosted trees, which take a different approach. Instead of training a bunch of trees in parallel, like the random forests, the gradient boosting trains them one after another. Each new tree tries to fix the mistake of the one before it. That usually means higher accuracy, especially for tricky cases, but the trade-off is that they can overfit if you don't fine-tune things like learning rate and tree depth. Also important. Okay, last slide, I promise, before the results, and I think this one's really important. So for the previous model, Ashish used SVM with bootstrapping since that data set was so small. Bootstrapping works by repeatedly resampling the original data set with replacements to create many training sets. Because of the overlap in the samples, each bootstrap model typically sees most of the data multiple times and can give a fairly optimistic view of how well the model performs. It's a bit like testing your model on data it's already familiar with. So we use a bootstrapping in 2023. But on the flip side, the k-fold cross-validation splits the data into k separate groups or folds and tests the model on each fold once while training on the rest. So I added a little graphic to explain that right here. Um, since each model is tested only on truly unseen data each time, this gives us a realistic estimate of the generalization performance. We also make sure the splits are stratified, meaning each fold has a balanced number of responders and non-responders, which is super important for an imbalanced data set like ours. So first I tried bootstrapping just to mimic what they did in 2023, but then when I got to the random forest and gradient boosted tree, the AUCs didn't look realistic, which you're about to see. So I did some research and hypothesized it was because of the duplicates of samples between training and testing. It wasn't as optimistic in the SVM because the SVM by nature is built linearly to prevent the overfitting. Therefore, I integrated the cross-validation approach for all the models just to have consistency and tested them in parallel. So yes, there's going to be a lot of data, but bear with me. I'm going to have a summary table at the end. Okay, so we have data. This is the original SVM model where we tested 6 different sets of data. Each set corresponds to the graph. Each set imports a different combinations of features from the new features table. So set one, which is this one right here in the top left, is just the left ventricle strain metrics. So this is left ventricle global metrics, left ventricle regional metrics, just anything left ventricle. This was the one that was used in the model that was presented in the paper in 2023 by Ashish. The second set, which is right here, is left ventricle and clinical features. So these clinical features are usually what's available to the clinician before CRT. So this is what was presented before the paper in 2023, but this is integrated with the left ventricle. This graph right here in the top right is just the left atrium. So again, we're just doing left atrial global metrics. So these are the ones I computed today or for this project. And in the bottom, set 4 is left atrium with clinical. The middle right here is left atrium with left ventricle without any clinical. And then this last one right here is left atrium, left ventricle, and clinical. So essentially all the metrics. So as you can see, the AUC is decent for all, but the best uses all the features in the bottom right with this AUC of 0.99. Again, still kind of hesitant with the bootstrapping results. I couldn't replicate exactly the same results as Ashish because I didn't use the same seed, and I think some of my parameters for the bootstrapping were a bit different. I think he got a 0.87, but I got a 0.88 AUC for the left ventricle. But ultimately, this is showing us the trends with what happens when we add more variables, and just using the left atrium by itself isn't sufficient for this use case and this model. Okay, moving on to the next result. So here, same results, bootstrapping results with the SVM, but now I've created scatter plots in which the y-axis is the patient's change in end systolic volume. So at a cutoff of minus 15%, which corresponds to this horizontal line, patients are defined as responders below this line and are represented by blue plus signs. And then patients above this line are true non-responders and are represented by red circles. The x-axis is the score assigned to each patient. In MATLAB, I defined the score as the Youden threshold, which is the score that maximizes the difference between true positive and false positive rates. So this differs from Ashish's methodology for assigning the threshold score. I think he used a threshold that maximized the geometric mean of true negative and true positive. The reason why I did this Youden threshold, I didn't know what it was. ChatGPT helped me, but I could do it consistently between all my learning models. So I wanted to do the Youden for all the SVM, the random forest, and the gradient boost. So that's why I just kept it consistent. And then, so patients left of this vertical line were predicted not to respond to CRT, while patients right of the line were predicted to respond well. And then I've also added patient counts for each of the quadrants. So if you had a perfect situation and it predicted really well, all the blues would be in this corner and all the reds would be in this corner. And then you would have none in the false positive, true, false positive, false negative boxes. And then again, each scatter plot represents the 6 sets that I presented before. All right. Moving on. Random forest. Hold on. Just to show you all the data. So here you can see the bootstrapping results for the random forest model. As you can observe, these AUCs are quite high. This suggests that the model can almost perfectly predict response to CRT. This may hint that the model is overfitting. We don't know that for sure yet, but you can see here that we're getting AUCs of 1.00, which is pretty spectacular if that actually is true. And then here are the associated scatter plots, which again show a very good prediction for all sets of metrics. And then moving forward to the gradient boosted, we got AUCs of 1 for everything. So I knew this was a little too good to be true, at least I thought, since I got a AUC of 1 across all metric sets. And here you can see the perfect case scenario for the associated scatter plots, like I said before, with all the responders predicted to be in this quadrant and all the non-responders predicted to be in this quadrant. But again, a little dubious of the results. And that's why I had to do some research figuring out what was causing this. What can we do to not be a little too optimistic with the model? So that's why we went to the five-fold cross-validation results. So I did everything exactly the same, but now instead of doing the bootstrapping with replacement, I did the five-fold cross-validation. And just to summarize, or just to repeat myself from before, now we're not seeing the same data in the testing and training, which can hopefully provide more reasonable AUCs that we trust. So here are the results for the five-fold cross-validation for the SVM. Again, this is the original model used in the paper. And if we look at this, the left ventricle, it dropped from 0.88 to 0.71. And then if you add clinical, you increase it. If you add atrial, you increase it even more. So about the same trends that we've been seeing before. Here are the associated scatter plots, which with again much more reasonable results. And then now we've entered pretty new territory, which is now we're using the new random forest technique with the cross-validation approach for all 6 combination of metrics. To note, the left atrium by itself is not performing well. It's actually worse than chance.
Yeah, you just have to do the opposite of what it tells you to do.
Yeah, exactly. Yeah, exactly. But the good news is that it did improve the results confounded or combined with the left ventricle and the clinical, which is pretty decent. But in this one specifically, it didn't do too much different from just the left ventricle and clinical. So in this model specifically, left atrium, the extra work for incorporating those metrics isn't absolutely necessary in this model.
Right.
Here are the associated scatter plots. And then now the very last 2 slides for results. The last iteration results, I'm showing the gradient boosted tree model with the five-fold cross validation. So this is actually our highest AUC value with the cross validation results here. I know this also says 0.8, but I'm about to show you this one's actually a tiny bit higher. And then here are the associated scatter plots. So here we summarize everything. At the top, you can see the AUC results for all combination of sets, models, and validations. To conclude these findings, bootstrapping may have caused some overfitting, especially for the random forest and the boosted gradient models, which is why we tested the five-fold gradient or cross-validation in parallel. These results may have been more realistic for this retrospective study, even though left ventricle plus clinical results performed quite well. When appended with the left atrial strain, this slightly improved the performance. Although when adding left atrial strain metrics to left ventricle strain metrics alone, this improved the results when bootstrapping, this worsened the results when cross-validating. And then the logic gradient boosted tree model almost always performed best, although it most likely was overfit when using the bootstrapping approach. And then all that said, I bolded the highest AUC on the cross-validation side. In my opinion, again, I haven't looked at these in too much detail or done any sort of checking for overfitting or anything. But all that said, my opinion is that the logical gradient boosted tree model with all the metrics should be used as a predictor model for CRT response. And again, I didn't do a PCA to see what variables were really driving it, but that's something you could do to really isolate which variables you were using and which columns in the features table you were importing. So to end, some possible next steps could be to do a much larger cohort so we don't run into the issue of having to bootstrap or cross-validate. We could do a traditional 40-40-20 split for train test validate. And then these other directions, they were mostly from my conversations with you, Dr. McVeigh, but we could incorporate additional metrics to the model, such as the myocardium. I also acquired this data after smoothing the 40 CT data. If we're able to, a next step could be trying to do this from the raw data, if we have a cool model that can do that. And then lastly, we could use higher resolution lead placement meshes to better predict responses and placement of the leads. Although I didn't focus on this for this project, this was discussed in the original paper and could be another future direction. So I've also included the AUC of the last model, which I thought was the best here. But otherwise, that is it. Thank you everyone for listening. I can take any questions.
Great. That was a tour de force. That's a lot to take in all in one go. Do you think, but I mean, part of the problem obviously is when you're trying to do the validation model with that number of patients, right? With where you only had 82, right? And so your cross validation is a little bit small, and therefore you start to get these strange looking curves, right? Because they, as individual or little groups of patients move this way or that on your scattergram, the curve changes a lot. Do you think if you had, say, 400 patients or whatever we have 300 or something patients, that curve is going to start to smooth out and give us a more.
Yeah, I think to echo what you just said, every time I ran it, it was a couple percentage points up and down based on the random seed. So I think the results will be more consistent and the curve will get smoother if we have
Yeah.
more patients. Yeah.
Oh. And then from the clinical data, was there anything in the clinical data that would map directly to a correlation with the atrial data? Do you know?
Yes. Let me look at I have the Excel sheet up with the features table. So again, even though I said we use all the clinical features, I only use the columns that Ashish used. So even though we have like
Mm-hmm.
one columns, only some of them are used. So I don't know for sure if this was incorporated, but there's a actually no, maybe there's not. There's RV diameter. It's not, I thought it was LA
Oh,
diameter
okay.
from
Yeah.
Echo.
Okay.
CAPSI, max TRPG, hemoglobin, QRC, so maybe QRC
Yeah.
could have some left atrium. Sex, ICM. What's ICM? ICM,
What
I don't
is
know
it? Yeah, I've forgotten.
I don't know what ICM is. MI, it's binary, so I guess if they had it,
Yeah, it's
if
had a
they
previous
had it,
one. Okay.
cabbage score and then perm aphid. So those are all the metrics. But again, I have to look in my MATLAB script to see which columns were imported, but I don't know if any of those suggest direct
Yeah.
correlation to
So
change.
AFib might, and also TAPSI might correlate
Okay.
a little bit with left atrial function. Okay, great. Thanks.
Bye,
Thank
guys.
you.
Thank you.
Okay. So, hello, everyone. My name is Benjia, and my partner is Diana. And our project is on calcium granule detectability and motion. Okay, so first to go over the background a little bit again, this project focuses on cardiac scans of like coronary artery calcification, which is the buildup of calcium in coronary arteries, and this can be caused by atherosclerosis, which is plaque that accumulates because of various reasons like high cholesterol, diabetes, etc. And these plaque, they can either stay as plaque or they can like calcify, harden to these granules. They lie like inside your artery along the wall, so it can narrow the artery, restricting blood flow. That could trigger like fatal results like heart attacks and strokes. And these are measured in like Hounsfield units, but also Agatston scoring, which is also based off of Hounsfield units. Um, and you can see like these are like the ranges that for the scoring.
Our motivation for the study was based on this paper where this group looked at high resolution micro CT imaging for characterizing microcalcification detection in breast CT. And in coronary CT, cardiac and respiratory motion are unavailable or unavoidable, and they likely blur any small calcification. So this reduces the detectability threshold. And so our aim was to extend this group's methodology by simulating and validating the impact of motion blur on calcium detectability in coronary imaging. And so this group just looked at static um, microcalcification, and so we're looking at motion. Our objective is to look at how does coronary artery motion quantitatively affect the detectability of small calcium granules and what amount of motion can obscure detection beyond clinical threshold.
Okay, so I will go over our first simulation, which is 1D line profile. So this simulation basically is us using MATLAB to simulate this behavior of like taking a CT scan while your calcium is in motion. And we do this by doing the radon-based CT modeling across 180 degree of CT acquisition. And here we use 0.5 degrees of angular step size. So there's a total of 360 projections taken. And we do this across 7 velocity values, and we use 4 different phantoms to do this, which are square, circle, rectangle, and Gaussian dot. Okay, so to just go over some numbers, we chose our scan to be 1024 by 1024 pixels. So that's the size of our matrices in MATLAB. And then we defined the field of view to be 300 millimeters, which is within the range of like what it's used for cardiac scans. So that gives us a resolution of 0.29 millimeters per pixel. And since different CT machines have different like rotation time and speed, we looked up all of them and decided to go with Siemens CT, which rotates about 180 degrees in 125 milliseconds. And they also do 360 projections in those 180 degrees. And then to kind of gauge out like what velocities we should choose, we looked up like, the average velocity the RCA kind of moves at, which is around 69.5, give or take 22-ish millimeters per second. So these are the values of the velocities that we used. And then this is the calculation used to convert it to pixels per projection, which is used like in the MATLAB simulation. Okay, so
Can I
you
ask
might,
can I ask a quick question?
yes.
Um, on the setting of the total number of projections, it says here Siemens says 360 projections in 180 degrees.
Yes.
So that's 720 for the full 360. Where did you get that number?
I looked it up online.
Okay.
Yeah.
And it came out of one of their like white papers or something like that? Because I would have expected that number to be higher. It's
Oh,
Yeah, I would have thought it was like, I don't know,
okay.
a
Yeah, maybe I should
thousand.
double check
I don't
that.
know, but
Okay, yeah, maybe I should go back and double check that.
okay, cool. But
Yeah.
you did look it up and came up with that estimate.
Yeah, yeah, yeah.
That'd
Yeah.
be good to get the source. Okay, great. Thanks.
Okay. Yeah, so for the visualization, just kind of just go over how we modeled this motion. We started with, so we basically made a frame or a matrix with each of the positions. So this left one here shows like where this phantom starts at. And then we tested this with like different velocities, right? And then you might think that like the velocities are very small, those values. So it's bound to like move a fractional amount in like one step. So how do we model that? And the solution is like there's a function in MATLAB that's imtranslate, and it can like interpolate the or I guess like when you move a fractional amount, it can interpolate like that value and figure out what's the value in that half step. And it basically does this through like averaging, taking the average between the two pixels on either side of that half step. So that's what you see in these gray areas. This is the 15th position, and it's moved 2.8 pixels with this velocity. And then this is the 21st position to just show when it moves an integer amount of pixels, it's just the phantom moved over by that many pixels. Yeah, and another point to make is that since they're moving at different velocities and this time that's taking the CT scan is constant, they're moving different distances. So that was a loophole that I made a mistake on during the simulation. So this is like to kind of point that out. And then the how do we synthesize all the data into one final sinogram? Basically, when you take one projection at each angle, and then you get a 1D data, and then you put that into the final sinogram. So each projection is one single column, and then you could just kind of put them one after another. And then after you get 360 projections, they make that final sinogram. And then we do the inverse radon to get the reconstructed image. Okay, so here are some results we got for the different shapes. So I just chose like a few velocity graphs to show you like the trend. So as we can expect, faster, higher velocity will result in a greater attenuation in the intensity of the calcium as well as more motion artifacts. So as you can see, this does not look like a square anymore. It's because when the square is moving, you're getting these different projections and they kind of make up this curve shape. But as velocity drops, you see that that gets thinner and thinner and it approaches a almost perfect reconstruction picture here. But this is a very, very low velocity value. But this kind of shows the general trend. And then for a rectangle, it's very similar to a square, but maybe a little bit more smearing since it's not, perfectly like the same size, same length of the side on all the four sides. And then this is Gaussian, and this one has the most artifacts, and it's due to the fact that it does not have, a clean cut edge like the square and rectangles. It dies down gradually in the Gaussian curve way. So you have a lot more interference and stuff when you do the projections. So it's very blurred. But we see a pretty good reconstruction here at the low velocity as well. And then also another thing to take note of is the Gaussian, it has very big attenuation. Um, and then Diana will go over that effect later in our second simulation.
So can I
Yeah.
just pause for a sec on this? If you were to, can you put your mouse up on the slide? Oh, great. If you were to point where it starts and where it finishes on, say, the top left one,
This
I'm
one,
thinking it starts, the object starts where?
um,
Like
it
in
starts,
the velocity, like in the true, you know where it is on that image across the whole acquisition. So just drag your mouse from where it started to where it ended.
let's see. I think it takes a projection this way. I think it starts at like pixel 130, right? Like that's where I set all of them to start. And so I guess it would be around this area, but then it moves horizontally. So when it rotates 180 degrees, since the road doesn't change.
So is it possible to go into instead of what a presentation mode? Can you go back to the raw slide mode?
Yeah, like this.
Yeah, now click on that one on the top left
Uh-huh.
and then go to zoom. Like zoom that. Do you have a zoom in there?
Oh, like
Yeah, yeah.
this?
Yeah, just keep going. Like I want to go right up to where the artifact is. Okay, keep going, keep going. Okay, now and keep the axes in view. Okay, so where's 135?
130 is like maybe around here.
Right around there. Okay. So you think it's not starting at the far left edge of that arc. It's starting somewhere down the arc, right?
Yeah, that looks like, yeah, if we were to pinpoint it around 130.
Okay. And then it's interesting, right? The motion is horizontal, right? But the artifact is like this smiley face, right? So it's actually quite a lot different than other imaging modalities in how this thing, you know, works. And okay, that's great. And I guess Diana, you're going to talk about how bright this smiley face thing is.
How would that change? Like at what point would your reconstructed image drop below 130, which is like the threshold to calcium detection? So this is 150. Basically, with the velocity ranges we looked at, they all drop below 130 in those like velocities. And then as we go higher, and I think the initial intensity, I guess this would represent like how dense or how big your calcium is. So I guess it makes sense, right? That if it's bigger, you would probably be easier to um, detect it. So this is if you start out with an intensity of 250. So you can see that the Gaussian would drop first. And then for initial value 400, they basically all stay up on top. And then, so this one looks like, it was like the middle range. Then we tried a couple more velocities to just see when the others will drop. So these like are the points that it would drop below the threshold of 130. So I guess the conclusion for like the simulation one is that it really depends on like a lot of different factors, like your velocity and also the size of your calcium. Um, and then for the phantoms, the Gaussian and square really had the greatest attenuation, and this graph also proves that as well.
So that's interesting. Okay. So the slope or that rate of decrease is fairly importantly dependent on the shape, especially for the Gaussian, huh?
Right,
It seems
right.
to fall into line once you get to a certain velocity. Okay,
Yeah,
great.
yes. Then, yeah.
Thank you, Pangia. Now we'll look at some patients that have calcium in their coronary arteries, and we'll try to see what motion looks like and how it affects the signal. So our goal here was to quantify how individual calcium granules displace over the cardiac cycle in clinical CT. We chose a reference phase, and we chose between 75 to 80%, which corresponds to like the late diastole phase. This is where there's very minimal movement. And our measurement method was we placed a 3D ROI on the same calcium granule at all the phases from 0 to 90. And then we recorded the XYZ coordinates and the amplitude at each phase. Then we computed the Euclidean distance at each phase's coordinates to the reference point. So this is case one. I'm just showing here on this slide two key snapshot freeze reconstruction side by side. So one is at 75% of the RR interval on the left, and then one is at 50% here on the right. And you can see the accompanying like ECG traces. And here, essentially, what you're seeing is that each snapshot freeze will correspond to a specific moment in the patient's heartbeat, which in turn controls like the cardiac cycle and where the CT data is acquired. So on the right, if it's reconstructed at 75% at the RR interval, that means the scanner waited until 75% of the way through one cardiac cycle. And this is roughly late diastole. And this is right before it freezes. And then on the right, it's reconstructed at 50% of the RR interval, which is approximately mid-systolic phase of the heart. So at 50%, the R interval is halfway between the two R peaks. Okay, and then here we are seeing for the same case, all the phases from 0 to 90. So at the top one, this is phase 0, and this is right at the start of the R peak. So this is the start of systole. And so the lesion would have shifted maximally from its diastolic position. So we chose 80% here to be our reference point because that was where we saw the least movement between the calcium that we chose. So the calcium here is indicated by this point that we labeled, and it had the highest amplitude between all the phases. And then in phase 10, here by 10%, the ventricle is still contracting. This is early systole. And then phase 20, this is mid systole, so similar displacements. And then at phase 30, we're seeing it's entering early diastole. And then by 40%, you can see the plaque is like nearly returning to its late diastolic spots. By phase 50, so the bottom left now, this is mid
Are
diastole.
you able to use the cursor or the pointer in your, is it available there? There you go. Oh, great. Perfect. Thanks.
Yeah. Maybe I should, yeah, I'll point it as she says.
Okay.
Okay. So we're now at 50. So 50 is the bottom left, first bottom left, and then phase 60, the plaque is still near. There's a tiny bit of downward motion as the arterial kick forces more blood into the ventricle when you're at phase 60. And then phase 70, you're at late diastole. This is just before the arterial systole finishes. And then second last one is phase 80. So the heart here is almost at the next R peak. And then phase 90, you're very close to the next R peak. So here, so yeah, so again, so we just chose, we picked one calcium granule spot and we measured everything from the reference point, which was 80.
And
And
so
then the next
are
slide.
you between each one of these, are you moving the slice to find which slice that piece of calcium is in?
Yes.
Okay, so you have to track it in the slice as well as on.
Yes.
Okay.
Yeah. Yeah. That was the tricky part for all of these cases. Okay, and then next slide. So here we're showing we have two graphs here. So we're showing plaque velocity curve. So we're seeing how fast the calcified lesion is moving in millimeters per second at each gated phase when you measure its displacement relative to the 80% and diastolic reference. So at each snapshot phase, like 0 to 90, we manually recorded how far the plaque has shifted compared to its 80% image, where we assume zero motion. So interestingly, you can see here, this on the right is the displacement from the 80 phase. When you're at 2 millimeters, so this is approximately the 40% phase, the plaque was decelerating out of systole. So here on the left, you can see it's like 4 millimeters per second, and it produces severe blur. So the peak amplitude drops to like around 500. But then here on the right again, when you look at 4 millimeter displacement, this is 30% phase. The plaque was steadily moving into diastole. And so then you can see back on the left graph again that we're at now like 5.7 millimeters per second. So producing moderate blur and a much higher HU as opposed to a smaller displacement. So it depends again, like where you are in the cardiac cycle will depend how much motion blur there is. We were also looking at how there could be partial volume effects. So whenever a small lesion straddles two or more voxels, then each reconstructed voxel can see a mixture of calcium or soft tissue, and so its peak amplitude is dragged down. And then here is another case study that we saw. So here in this case, the image is required from 40% of the R interval. And so 40%, the heart is in late rapid filling, early deceleration phase of diastole. So it's immediately after end of systole. And then on the right, we're looking at 70% of the R interval. And this is when the heart is in late diastole. So in this case, we chose 70% to be our reference point. And so we just looked at from 40 to our reference point, how much did it move? And we saw that the Euclidean distance was 7.9 millimeters. So it moved quite a lot. And then next slide. So what we learned from this project was that motion blur reduces the detectability of small granules. And then in Sim1, as velocity increased, the apparent width and peak intensity of the Gauss and step function phantoms both broadened and dropped below the threshold values. We saw that the square and phantom were easier to detect at moderate velocities, and that the Gauss dot lost about 20% or 25% of their peak HU at lower velocities than uniform shape. So you can see here that the low contrast spots are the most vulnerable. And then for partial volume effects, we can see that the calcium granules moved between 5 to 8 millimeters between end diastole and peak systole. And when the granule shifts greater than 1 millimeter out of its reference ROI, its measured HU dropped by 10 to 15%. For future work, how to extend this, there are so many things that we could add on to see what are the confounding factors with all of the different cases for motion blur. We thought it'd be interesting to incorporate realistic 3D motion models. So to extend simulation one to include rotational and out of plane motion. So like pulsatile radial expansion of the coronaries and not just pure horizontal motion. We were thinking it'd be interesting to correlate, to understand whether BMI, chest diameter, coronary vessel torosity affect how little motion suffices to blur a lesion under the threshold. So for this, we were thinking like, can you have a set of correction factors? Like for instance, if a patient has a BMI over 30, then they'll require motion less than 0.8 millimeters to, reliably detect any sub-millimeter calcium versus a lean patient. Can they tolerate maybe like 1 millimeter motion? And then also the impact of vessel orientation and motion direction. So in both Bantam and patient data, can you assess calcifications along the vessel axis and do they differ in detectability in the different orthogonal, if it's orthogonal to motion? So which orientation is most vulnerable, we were thinking about. And here are our references and our data set from our patients came from Professor McVeigh. Thank you for your time.
Okay, cool. That was great. Can we go back to the graphs? Diana, your graphs that you showed. Okay, those two graphs.
Mhm.
Oh, the next slide.
This one. Or oh,
No,
the graphs, the
the,
graph.
the one that had, that's it. Those graphs. Yeah. So this is the displacement from, and so it goes out to 9 millimeters away. Measured peak Hounsfield unit. Okay. And so obviously the I guess this is I'm trying to figure out what's going on with this really low one here. Is that systole? That's where it's like really moving fast first. So it's
At
display.
2 millimeters?
Yeah, like I'm looking at the left, I'm sorry, the right orange curve
Yeah.
at the point where it's 2 millimeter displacement. So we have
Yeah. This is at
12,
like 40% phase.
that's at 40%. So that is either that's probably not when the heart's contracting, but when it's refilling, right?
Mhm.
So in terms of the heart cycle, I guess there's a drop in amplitude at the beginning, and that's that first dip from 1200 to say 900, right?
Mhm.
And then it goes back up as the heart is in systole, where the displacement, no, that doesn't make sense. I don't know how to where
It
that.
would go at 4 millimeters, it would go now into 30% phase because our reference point is 80%
Yeah,
phase. So that's the highest amplitude. So then here it would go into 30% phase. I mean, we were trying to rationalize it. I think the issue is when you pick a reference phase, then you have to see how from that reference phase 80, how much is it moving like between all the phases.
right.
But it was tricky to
Yeah, I think
quantify.
another perhaps a simpler way to plot this data so that we can understand it more viscerally is just do it in time, right? And then if you do it in time, uh, we kind of know where the peak velocities are, right, in time. We know that the peak velocity is during contraction, and we know when it opens back up, and then it goes phase. So you would see it decrease in amplitude when it's contracting, and then the amplitude would come back up when it's in systole. Even the displacement, the relative displacement frame to frame is probably the thing to know, because that's going to be proportional to velocity, right?
Mhm.
So, okay, be that as it may, there's an extraordinary decrease, right, in amplitude from 1200 down to 500 in this patient.
Yeah.
And then that fractional decrease we saw from the velocity data, um, depending on where you start, where your HU starts, you're probably going to see the same fractional decrease, right, for that velocity, I guess. Do you think? So if we started at 600, it would have gone down to 300 or whatever the relative change is, I guess.
Hmm. Hmm. I
Um,
think if you have like 0 to 90, it'd be good then you can see more patient to patient when you have all the phases, but for most of them we just had 70 and 40.
I
But
see.
even with 70 to 40, you can just see like a dramatic
Different.
motion, yeah, distance.
Okay, cool. Any questions from the class? Thanks for doing that. That's really good.
Thank
Um,
you.
okay,
Thank you.
good job. Okay, next. Who's up next? We've got I don't know. Let me find my.
I think I'm next.
Oh, you're up now. You're up next.
Yeah.
Okay. All right. If you can take the screen and start, that'd be great. Thanks.
Can everyone see my screen?
Yes, I
Okay,
can.
let me open it up. Uh, Hi everyone. My name is Nyamishi. You can call me as me. And my project for the class is gonna be about balancing noise and detail for by using like AI powered denoising in clinical image. So first, I'm going to talk a little bit about the background, which is computed tomography is indispensable in modern diagnostic, but yet it is exposed to patient to ionizing radiation, and a low dose of CT technique aim to mitigate radiation risk, but increasing noise from reduced photon count, diminish image quality, and diagnostic confidence. Traditional noise reduction feature that we can discuss is gonna be like Gaussian or median and uniformly smooth image, often like blurry, subtle, yet crucial anatomical structure. And this limitation raise a pressing need for advanced denoising strategies that maintain diagnostic quality while effectively reducing noise. So like the image I'm adding into this slide is one of the image using traditional noise, which is using Gaussian to be able to like denoise an image. On the left, as you can see, is the image that is having like noise and we cannot really like clearly see the structure. But on the right is gonna be an image is being used to denoise by Gaussian. And then because of that, we're having a convolutional neural network, which is short for CNNS, as an offer for promising solution and different from previous denoising technique that apply uniform smoothing. CNN can learn complex data-driven pattern that differentiate noise from true anatomic structure. And CNN is suitable to address the unique challenge of low-dose CT image because of this project is aimed to investigate whether CNN-based denoising method can effectively suppress noise in low-dose CT image while preserving clinical relevant structure. And with this analyze and research is aimed to contribute to safe imaging practice and improving diagnostic accuracy. And I want to like bring like for my project, I want to like talk about like how CNN based denoise can kind of like improving it because like as I search for a scholarly article and stuff, I only see that they kind of like focusing on one separately AI and then train it up instead of like having a clear roughly research of like comparing two AI together and trying to see how they are effective in denoising the image. So now we're gonna move to our research question and hypothesis that I having for my project. And with the interest, the research question I am construct for this project is can CNN based denoising methods suppress noise in medical image while preserving clinical relevant structure? And then along with the question, the hypothesis that I have is CNN-based method can outperform the traditional algorithm by distinguish noise from anatomy. And this question is being asked due to the aim to address a critical gap, which is can deep learning-based method CNN effectively mitigate this trade-off and preserving both diagnostic quality and patient safety? And majority of the image that being used in this slide will be relevant to cardiovascular, and I will go through the next where we gonna like observe where we're gonna like obtain our data from. So when we're moving on to our data and method, so the data I'm relying on the AAPM low dose CT grand challenge, and to achieve the result, I utilize like two public data set, which is containing pair low dose and normal dose CT image from the AAPM low dose CT grand challenge and the Mayo Clinic. I choose this data set because they provide original high quality image along with a low dose scan, allowing us to like train and evaluate our model to control real world data. And this pairing is like particularly important in cardiovascular image, where accurate visualization of subtle vessel structure, plaques, and then myocardial boundaries is essential. And I also, for the algorithm, I also like relying on like uh, available research paper related to UNET and RED, where I just only pick one related um, scholarly article and I try to like implement on their algorithm. And then so for the CNN model, we focus on to establish architecture, which is UNET. And then the other one is gonna be Red CNN. And UNET was originally developed for segmentation tasks and used skip connection to preserve like spatial context and fine anatomical detail, which is especially critical for visualizing cardiovascular structure like coronary arteries and cardiac chamber. And then for the red CNN, directly targeting low dose CT denoising and is particularly effective for maintaining the sharp transition seen in vessel wall and myocardial boundary. Circling back a little bit to my proposal presentation, instead of just kind of like focusing on UNET, Red CNN, I also used to bring up about the DNCNN, but for our final project, I decided to take it out because I feel that I don't want to like complicate it up and I just want to like focusing on like two part comparison only instead of like adding in like the extra D and CNN. So because of that, I decided to just take it away. And then for the method of kind of like how to evaluate it, like each model was trained using like the pair noise, like low dose and normal dose, like reference cardiovascular CT scan. And then we will employ mean square error, like MSE, as the loss function to minimize the intensity differences between the noise output and the ground truth image, and then ensuring that the model produce output that closely resemble the original clinically relevant image. MSE is particularly important here because it's penalized larger error heavily, which is essential for like accurately restoring subtle but also like crucial cardiovascular structure. And then for the we also like using like the Adam optimizer was also used with a learning rate of 1 and 10 over minus e for all model, and the Adam was chosen because it's combined the benefit of two other methods like the ADAGRAD, which is adapt learning rate for different parameter, and the RMS prop, which is effectively handle non-stationary object. And then the learning rate of 1 to the power of negative 4 balance learning speed, stability, and ensuring that the model is steadily approach optimal solution without overshooting or causing unstable training, which is critical for preserving the fine detail needed in cardiovascular image. This is also like another part of my method and how to kind of like evaluate it is I'm coming to after the method like my evaluation metric will divide into three sections: quantitative metrics, qualitative assessment, and region specific evaluation. Like for the quantitative metric, we're focusing on general quality metrics that are um, widely used in image processing, which is the peak signal to noise ratio and the structural similarity index. For the PSNR measure overall noise suppression effectiveness with higher value indicating better noise reduction, while the SSIM mimic how the human visual system perceives structural similarity. The SSIM is particularly useful for evaluating how well fine cardiovascular structure, such as like the coronary arteries, vessel wall, and then the myocardial boundaries are preserved after denoising. And then to further validate clinical relevance, we incorporate a qualitative assessment using a test-based CAD system. This clinical focus evaluation directly measure whether the image change introduced by our denoising model actually improve real-world diagnostic performance, and especially we test the CAD system performance on the noise image versus noise low dose image and normal dose reference image. And the CAD system was evaluated using like key clinical metric was its sensitivity, ability to detect true positive, and also specificity, ability to avoid false positive, and area under ROC curve, which is combine these measures to reflect overall diagnostic performance. I decided to kind of like change the qualitative assessment because when for the proposal assignment, professor has already pointing out the fact that it's not really like reliable if we just relying on radiologists to read the image because like um a little bit information might be different. So because of that, I try to change and make sure that like for the evaluation metric, the first step is just kind of like using AI and algorithm to address it instead of just asking like a real person to look at it. And then for cardiovascular image, like this evaluation metric are critical because it's subtle anatomy detail. Um, and by ensuring that noise reduction does not degrading the structure of the image in the image. And also like um also testing whether like noise image actually improve the CAD system performance. We aim to provide a comprehensive and clinical relevant assessment to the model utility in cardiovascular image. So because of that, I add in the other section, which is a region specific evaluation. Is that like make sure that like when we look at one structure or one anatomy structure, we just kind of like focusing on that first instead of just compare about like the cardiac chamber with the aortic arch, trying to make it like fair and accurate and kind of like similar. And now we're moving to the unit algorithm. So for this algorithm, I pulling this out from a scholarly article instead of like compute it up from scratch. The algorithm described in figure 4, as you can see right here. Um, figure 4 and figure 5 of the article detail on attention-based UNet architecture that enhance the classical unit feature extraction and spatial detail preservation for medical imaging application. So for figure 4, the diagram illustrates the overall architecture with an input image pyramid and a deep supervised output layer and emphasize the hierarchy learning of spatial feature across scale. This approach usually skip connection, preserves spatial context, and facilitates the integration of high-resolution local feature with low-resolution global feature, and thereby supporting improving visualization of cardiovascular structure. And then for the figure 5, it elaborate on the internal mechanism of the attention gate. And this gate operate by generating attention coefficient for each pixel, selectively emphasize region with high clinical relevance. And during the decoding process, and this process migrate the potential loss of spatial detail due to the repeated convolution and nonlinear activation in the network, making it like particularly relevant for the cardiovascular CT denoising task. That is the algorithm for UNet, and then here is gonna be the UNet model result. I'm gonna go from each model and their result first before I come into the other one so that like we can keep in mind like what are we looking for. And then for the unit result, the first result is showing that the model demonstrated significant improvement in image quality for cardiovascular low-dose CT image and the peak signal to noise ratio, PS and R for the UNet model showed an average improvement of like 5 to 7 dB over the original low dose CT image. And then the substantial increase in PS and R confirmed that UNet effectively suppressed noise while like preserving overall image fidelity. A critical aspect in cardiovascular image where small vessel and tissue detail must remain intact for accurate diagnostic. And then the structural similarity index, which is short for SSIM, also improved with UNet achieving SSIM score greater than zero point 0.9 on average, closely matching the normal dose reference image. High SSMI value indicate that UNet preserve fine cardiovascular structure such as like coronary artery boundary, myocardial wall integrity, and small vessel detail, and then feature that essential for precise cardiovascular assessment. And in terms of clinical performance, the CAD system test on the UNet denoise image showed that sensitivity for detecting subtle cardiovascular feature approach that on normal dose image. Specific CT also improved with reduced false positive rate compared to noise low dose image, indicated like UNet denoise image did not introduce false structure or artifacts. And finally, for the AUC, improved by zero point 0.1 to 0.15 compared to noisy image, confirm an overall enhance in diagnostic performance when using like UNet, the noise cardiovascular CT image. And then this is the picture to supporting the UNet result that was being mentioned. So like the unit denotes image consistent of preserved detail structure across like key cardiovascular area. I'm gonna go through like each figure, figure 1 and figure 7 more detail after kind of like went through roughly. The coronary arteries, cardiac chamber, and the aortic arch, and the model showed an ability to maintain like this crucial anatomy feature underscored its potential to support clinical decision making. And as you can see in figure 2, it provides insight into the overall architecture or loss function improvement used to enhance segmentation performance, indirectly relevant because the project also utilized unit capacity to preserve important cardiovascular detail while suppressing like the noise. So you can see like how it was kind of like showing out. And then for the figure 7 is directly compare segmentation result of UNet, attention UNet, and other advanced methods, showing how UNet perform in preserving structure in cardiac image, make it a strong visual support for UNet result claiming cardiovascular. Yeah.
May I ask a question? So this UNet result
Mhm.
is a segmentation or labels come out of this. And what I don't see is a comparison of the accuracy of those labels pre and post denoising.
Oh, so like the usually like this one it's just kind of like I didn't put like the compare like the before and after, but this one I pulled from a scholarly article using the code that they run to denoise an image. They didn't attach like the image like before they denoising out. So this is just kind of like the image of like after they have been denoising it out.
See.
And it's still kind of like they also like showing the feature and showing that like the unit after we running the algorithm that was being that's we kind of like I was like mentioned in other like slide, like they still gonna keep like their main goal, which is like the structure and the small anatomy. And
I
then
see.
this one is just showing how the unit, the basic algorithm that they having running, and then slowly they kind of like adjust and then add in more adjustment in it.
I see. So you started at 10, so you've done 18 minutes so far. Can you can you
Yeah, yeah, I
tie it
see.
up in 5 minutes or so?
Yeah, I'll try.
Okay, thanks.
Then now we're moving up to the ResCNN algorithm. So like for the it was designed to like denoise like low image, and then for this one, the algorithm first exact local image patch rather than using like pooling large to preserve like fine spatial feature essential in cardiovascular CT image, and the stack convolution encoder progressively suppress noise and artifact, and the convolutionary decode then reconstruct the image while shortcut connection between corresponding convolution and the convolutional. And this is the algorithm we use for the red CNN, and then we are moving up to the red CNN result one. So like the model showing like almost like similarity compared to like this showing a little bit similar compared to the UNet, but I will come up to the slide that we're comparing the both um UNet and CNN, right? And then this is the result for the red CNN. The figure 4 in the article, the figure 4 right here is showing sample input image and their corresponding segment output using the proposed red CNN-based approach that we mentioned earlier on the echo dynamic dataset. And this directly support ResCNN result by visually demonstrating that ResCNN-based method can enhance like cardiovascular structure like the heart temper while reducing noise and preserving essential feature and highlight ResCNN ability to maintain structural integrity. And then right now it's going to be a comparison between UNet and ResCNN. For compare, the UNet model has a higher PSNR improvement, which is 5 to 7 dB, and the SSIM score, which is more than 0.9, suggesting that is the best job at both reducing noise and preserving the fine cardiovascular structure like vessel wall and small artery. It's also excellent at maintaining overall image fidelity, make it particularly good for visualizing small detail in coronary artery branches and myocardium. And on the other hand, like ResCNN also provides substantial noise suppression with a PSNR increase about like 4 to 6 dB and an SSIM score above like 0.88, while its SSIM was slightly a little bit like lower than UNet. ResCNN showed great strength in preserving like sharp transition and clear boundary in cardiovascular structure. And this was especially evident in the region-specific evaluation where ResCNN was very effective in maintaining like clear vessel wall and myocardial edge. When we test them with the CAD system, both model improved sensitivity and specificity compared to noisy image, with UNet showing a slightly high overall AUC improvement 0.1 to 0.15 compared to red CNN, which is just only 0.1. And this suggests that both model enhance clinical diagnostic performance, but UNet has a slightly edge in overall structural preservation and diagnostic confidence. And now we're moving to the conclusion is showing that CNN based denoise specifically using UNet and ResCNN model can significantly improve the quality of low dose cardiovascular CT scan, and both model effectively suppress noise while preserving critical cardiovascular structure. And then the UNet achieving highest MSNR and SSIM value compared to the red, and also the red CNN also perform well, especially in maintaining sharp transition and vascular wall delineation. And then for the reflection and future direction, so for future direction, several areas we could be explored is to build on this work. One priority is to validate this finding with larger and more diverse cardiovascular CT data set, including image with different like noise profile and anatomy variation. Another avenue is to integrate clinical feedback from cardiologists and radiologists to refine the model output and ensure that they meet the real-world diagnostic need. And additionally, like exploring the combination of this denoising model with automated CAD tool provide a more comprehensive approach to improve image quality and diagnostic performance. And finally, is investigating real-time deployment of this model in clinical PACS system could help translate this promising results into routine cardiovascular imaging practice. And here is the citation for each segment. Yeah, that's it.
Could you isolate which, in your citations there, which paper was mostly referred to here? It seemed like most of this came out of one place, right?
Yes.
This is the main
Let
paper.
me pull it up. So I will for the paper that I've been using for the UNet model, I'm using like this two paper. One I'm kind of like read about the algorithm and the general paper UNet, and another one is I kind of like reading about how they interpreter about like the algorithm that they're running, but the result and the algorithm that I picked is gonna be on the same paper, which is paper number 1
Oh, okay.
right here.
All right, so
Yeah.
paper number
And
one.
for the rest CNN, I also pick on paper number 1 to similar algorithm and similar result.
And the AAPM low dose grand challenge data, was that used in paper number one?
Yes.
I see. Okay, great. Did you write any code or anything like that to run this, or you just reflected their results?
I just reflecting on the result. I did not run any code.
Okay. All right, great. Cool. Okay. Well, CNNs are great at denoising, that's for sure. I don't think we have to look at noisy images ever again. I don't know if they're true, you know. Don't know what the threshold is for that. Okay, me, thank you very much for that. So let's move
Before
forward.
we move, Dr. McRae, could we enforce a time limit? We have 17 teams and I have to leave by 11.
Okay. Um, sure. Uh, Shashank, are you going next
No, I
or
think
Our
uh,
team is last. I'm happy to wait if you guys need to go first, if Maggie's okay with that.
Yeah, I'm okay with that.
okay, that
okay,
would be great. Thank you so much.
Yeah.
thank
Thanks,
you.
guys.
Okay. Um, are you sharing screen or am I?
I can share. I can't tell which screen is sharing.
Well, I see
Uh,
a presentation. Looks like a Google Docs presentation on my screen, CHD background, current gaps.
Oh, wrong screen, but we can use this one too. That's fine.
There you go. Yep,
All
it's up
right, let's
now.
bring it back to the start. Okay. Hi, guys. My name is Ria. My partner's name is Shashank, and we're going to be talking about a model we built to help diagnose congenital heart disease. So just to do a quick lightning fast recap of our initial presentation, congenital heart disease is a very common birth defect affecting around 1% of lives globally. It is typically found when you're a child. Like fresh out of the womb. And people use cardiac imaging in order to diagnose CHD. MRI is often used because it has low doses of radiation compared to CT. And so that's like specific for kids. People don't want to put high dose of radiation in that quickly. And so the current method is currently physician-based in how to diagnose CHD. So this is pretty time consuming and it's also not standardized. So every physician, whether you're a cardiologist, surgeon, or radiologist, they all have different ways that they diagnose it. So it's not standardized at all. And so there's kind of like a need for a automated tool to extract and analyze the shape and function data of these MRI scans. And so that's kind of what we are starting to do here. So that kind of moves us on to our project objective. We want to create a machine learning based classification of um, congenital heart disorder or disease from cardiac MRIs. We use a database called Cardiac Atlas, which is a UCSD based database. And so all the data that we're getting for this is pretty fresh and pretty new, but it also wasn't supposed to be for image analysis. So we're going to talk about a couple of problems we ran into because of that. We did kind of narrow our focus on just tetralogy of Fallot versus normal MRI or cardiac MRI, just because we wanted to get one type of defect diagnosed before you can, use the model for other things. And so our long-term vision is developing one for multiple different types of cardiac defects, which once you have a pretty good model, you can do. Just a little bit more about our methodology. We talked about our data source. We extracted nifty images, and then we pre-processed them. So we're going to talk a lot about pre-processing in the next couple slides, but then we wanted to build a model and then evaluate that model. So that's a little infographic for that. So for specifically pre-processing the data, this is a complete pipeline overview. We started with just organization, so like taking the files out of the database and then organizing it by files and acquisition type. Then we did some grouping in order to create 4D stacks. So basically there are
I'll actually do the step one. This was how we grouped our files. And then we did temporal grouping. So we basically took these MRI stacks, so they're like height and width, and then they also had two more dimensions. So they had slices through the body, and they also had time. So with using that, we created a 4D stack that had time, depth, height, and width in order to kind of combine all of these and create heart volumes that we could run through our model. Um, this was a really big, uh, I guess, portion of our time that we spent doing this, due to the size of our data set, and being able to create these like in order as well. Um, Sorry, I realize I have to not show these slides. Okay, so then we took that volume, that 4D volume that we made, and we conformed it into a 3D volume in order to just select one specific time frame. So before, the different time frames were not really standardized between every single MRI, and so we had to just take one specific, like t=0, first frame in order to get our volume. So it's still a full volume, like a 3D volume of a heart, but it's just not going through time anymore. It's just at one specific time. So that would make it a little bit easier just to visualize the whole heart and get our model all the data it needs to understand like all the different spatial parts of this heart and structural issues in this heart. Um, yeah, we did this through center cropping, padding, and then also downsampling. And then we also standardized our output shape. And so sometimes like MRI's output, I think a couple of them had like 300 something pixel by pixel. And so we standardized them all to a 256 by 256 by depth
When,
data set.
when you say t=0,
Mhm.
was that always the first volume in your stack, or is it some other t=0? Like
It's the first volume in our stack.
I see.
There is typically
Yeah.
three
And we're
to
going to talk
five.
about why that is an
Yeah,
issue.
Okay.
yeah. There are typically 3 to 5 time points anyway, and they also all aren't aligned to a specific thing.
Yeah. Yeah.
So it was kind of arbitrary. And then
Which I was
finally we
very surprised
classified,
by.
yeah, we classified our labels, with 0 being normal, 1 being tetralogy of flow, just to pre-process it and put it through our model. And then our final data set was here's like the final breakdown of our data set. So we had originally 265 normal and 234 CHD patients. Once we were able to find how many of these can be created into these volume files and had enough data for that, it kind of went down by 100 on each side. And then specifically like our 3D files went down by a couple. So that's just like having enough data to create these t=0 volumes. And then in those, not all of them contained a specific type of view we were looking at, which was the four-chamber view. We chose this specific view because it has the majority of what the four um, structural changes are in CHD. So those are the ventricular septal defect, the overriding aorta, the pulmonary stenosis, and the right ventricular hypertrophy. So you could see those more in the four-chamber view than you can kind of see that in any of like the LVOT, RVOT, and two-chamber or SA view. Um, Additionally, they had enough data on the right side. You can see that they had enough data that um, we could put it through a model versus like something like the two-chamber view, which only had like 50 patients.
I have a quick question.
Yeah.
That is, you start with 267, and then if they don't have the full 40, you drop them out. So you're down to
hmm
161. And then you say, I don't need the 4D. I'm taking just one time frame anyway.
hmm
So why did you drop the
I thought of that as I was speaking it just now.
why
So
did we throw those out? We had that time
I
frame.
think originally we wanted to use the 4D stack, but we wanted to just try our model out with one time point to make it
No.
like easier to see if it even works. And so that's kind of why we started out with t=0. Also, I was going through all of the actual stacks, and some of them when you switch time frames, they aren't aligned properly. So we wanted to get our alignment down first, and then we wanted to continue moving
I
on. So
would
that's kind
also
of,
say
yeah, go
these
ahead.
are all 2D images,
Hmm.
and then we had to create a 3D image from a bunch of stacks. So using slice time, trigger times, and then like their locations, like combining them to form. Even then, they were not aligned. So it was just
Oh,
the.
I
So
see.
if you go to like the very last, the supplementary, Ria, if you
Yeah,
can go to
let
the
me,
very supplementary, you can see it.
Got it. No, I
there we
start,
go.
yeah, I start to see what's happening.
Like these you see what like we had to like they're completely like rotated for some reason by 180 between patients, which I don't know how or why. Even their or like DICOMs don't have that like information, and I
Hmm.
don't understand why that is the case. They should
Okay.
be from like a person who's viewing it, like a radiologist POV. They should all be aligned the same way, but
Yeah.
they're not,
Okay.
which makes it very difficult.
Yeah.
All right.
So it's definitely
Sorry.
for ease of use of the data. Um, let me head back. Um, yeah, that's kind of it. That's kind of why we chose the four chamber view out of all the other views. I will talk about what we want to do in the future, but it is definitely incorporating these other views once we can get a better model just for the information you can get from a four chamber slide.
All right. I can talk about the model that we used. So we ended up using a ResNet model. We thought of few different models, but ResNet 18 is a pretty standard model. It has some pros and cons over all the other models. It's relatively small. It has shown to be really good with medical imaging data previously in some medical. That I also find out that there's another model called MedicalNet that might be more better, but and that's what we're going to try to use next. But yeah, for now we just use a ResNet model. Um, Next slide.
Oh,
And so yeah, there's like so this is basically the comparison. Um, I didn't see. Oh, okay, so we trained our model for like a bunch, like 20 epochs. I would say, and I would show later that at least in our experience, I don't think maybe it's the data set and how we curated it, but we didn't think ResNet 18 was as good as it's claimed to be in the papers. But at least from online understanding, it's supposedly really good. Next slide. So yeah, so this is basically our final model. As you can see, it didn't do great. Uh, at least not that. So there was like a training loss went, and if you just quickly go to the next slide before this
mhm.
slide. So this shows the training loss and the validation loss and the accuracy. The training loss is going consistently down. The validation loss is not as much, which means that it's not fitting very well. Same with the accuracies, validation accuracies all over the place. Um, Training is still slightly going up. I think it's not generalizing well, partly because, and we're going to talk about like what are the issues, but I think partly because the data is, we still need a lot of structure in the data. There's a lot, like for example, the Z we made Z equals to 64 for all of the slides, even if it was like less or more. That required either padding empty images, empty slices, or like reducing empty slices. Um, uh, can you go back to the last slide,
Mhm.
previous slide? Sorry if my internet isn't unstable. Uh, Next slide, sorry.
Model performance, right?
Okay, so yeah, so as you can see, the performance wasn't great. Validation accuracy ended up being like less than 50%, so below random. Training accuracy was much better. It's again, I think we mentioned this seems like the model is just memorizing training data rather than learning generalizable parameters. Slide 16. And then if you go, this was our confusion matrix. Just again, if you can see here, same issue we're seeing, right? Like training great or decent, validation not great. Um, Next slide. Some more metrics or graphs to show. And then finally, we can talk about what are the challenges where I think, main challenges that we faced. So this pre-processing and trying to structure this relatively new data set was very challenging. I think it's the biggest part of our kind of work with this. And maybe in hindsight, we may have chosen something more structured, but that's how research goes. Um, uh, we had four big issues. One was image alignment issues. Uh, um, I would say uh, I was trying to find a image that we can like a standard image we can align everything to or normalize everything to. I don't know if we can find either we find it in the same data set or we find an external one too. There were resolution variability. For example, the four-chamber view sine versus four-chamber view sense takes images differently. The four-chamber sense is more like more detailed and more clear because I think it takes in parallel. It has multiple cameras in parallel, and it had like multiple Z slices, which got resolution down to 64. Uh, Before reshaping to 256 by 256. I have done this in the past with the like brain MRI images, where it has been fine. Um, in heart, maybe not, at least my understanding. Apparently, from what I understand, and then again, as we said, t equals to zero. We're discarding all of the other cycles for now, which means that, and it's possible that t equal to zero is not even like the CHT particular timestamp, right? We need to find the one which it shows us the exact septal or like defect that we're trying to look for. Next slide. So this is the big problem with the alignment problem. For example, and as I showed you in that three images stack, if they're misaligned, when you're trading something, what the trading or what the model thinks is the heart now is completely in a different location. I think we can fix this by adding, and I saw this in like I think they did this in this uh, when they were trying to the ChatGPT models when they were trying to no one can explain why they did it, but they did it and it fixed the problem of like alignment of like for example text. So I think it can help us the same way applying random rotations during training. Um, we can also, as I think Dr. McRae pointed out, we can, instead of doing like the whole slice, we can add a bounding box and just
Mhm.
focus on the heart itself, um, which can maybe help us more with like, it doesn't matter as much with the alignment. Uh, and then finally, I think uh, we can um, combine multiple cardiac views. So as we said, this is only the four chamber view. It might reduce our data set, but it may help with the spatial orientation of the. I think this D stack helps with that, but maybe another chamber view will help even more. Next slide. The next big challenge was resolution and quality variation. Um, the sign versus sense versus other sequences. I feel like mixing maybe we should just try if higher quality because these are faster scans, right? And they have for example 160 slices in Z-stack. That may be better than the sine view because just the sine view because it has like maybe 58 or like 60-ish views only. We did try to normalize it to 0 to 1 values, uh, but I think yeah, forcing them to like this resolution. I personally don't think it's that big of an issue, at least in the XY direction. Z direction, maybe not in the XY direction, but not an expert, at least from my experience. Next slide. Finally, so the Z depth standardization was an issue. You're losing a lot of anatomical detail and resizing. You're creating these non-biological artifacts that may the model may train on. There's distortion. So many different issues, I think. Again, I feel like we should have used a more standardized data structure or just nifties because at least and I think one of the bigger issues was in the data set when they have tetralogy of Fallot, they had nifty images in them and they had labels with more structure, but they didn't have that for the normal CMR patients at all. So the normal CMR patients only had um, DICOMs, raw files, and just slices, which I think was one of the biggest issues we found. Otherwise, it would have been so much easier to just train normal versus and final slide or second last challenge for time equal to 0. Um, we lose a lot of diagnostic information. There's as mentioned, right? There's wall motion abnormalities. There's, for example, when you're going through time, you can see the systolic or diastolic differences. Maybe that's something you would notice in in a tetralogy flow patient. Uh, versus like uh normal patient. It could also be that for normal patient, time equals 0 means something else, versus for a tetralogy flow patient, the time equals 0 means something completely different. Um, so uh, so yeah, I think finally, I think this was maybe we can use some sequence modeling or recurrence models that adds some time temporal axis as well.
Yeah. This last slide mostly is future use once we are able to get a better model for this data set specifically. The data set from Cardiac Atlas involved a lot of, or a couple of patients had flow data as well that they had recorded. So it would be good to potentially incorporate flow as like a separate side model into this model, like, future. But the first thing would be able is to get the multiple MRI views. I think that would be best before we head into that direction as well. But it definitely seemed like this data set was used for flow analysis. That's yeah. Um, but yeah, that is our presentation. Uh, do we have any more questions?
I would say just structuring the data, I've in the past at least, it has taken us like when I was working on like brain MRI images, if it was this unstructured, it would take like 6 months to in a year to just structure and get it to like into a format that's trainable. We jumped the gun on that a little bit where we didn't realize how how new the data set is.
Yeah.
No, I mean, hearts are very, you know, they have very variable morphology, especially congenital diseased hearts have
Mhm.
remarkably variable morphology, right?
Yeah.
Yeah.
So part of
Hmm.
the fact that you could flip a coin just as well to get your decisions is probably reflected in the fact that the slices, even when you got everything ready and you picked your four-axis slice, if it didn't obtain the critical features for
Hmm.
pathology of flow, like,
Yeah.
basically the pulmonary artery and the septal uh, hole
Hmm.
and everything.
Yeah.
I just
Defect.
didn't see them, and then it would just call it normal, right? So it's
Yeah.
sort of a luck
Yeah.
thing. So I think this would have to be done with 3D probably, and so that you
Mhm.
would have to train on like and agreed you'd want to normalize amplitudes, you'd want to normalize spatial orientation at least, right? So that
Mhm.
you had some kind of systematic way of putting the same orientation into the network,
Yeah.
which is really hard to do, right? I mean, we've
Yeah.
we have networks that'll take data and give you the traditional reorientation of the heart. Like it just looks at the
Mhm.
heart, goes, okay, here's the apex, here's the base, here's a rotation to get the, the right thing, and it puts it in that view. But they're all really normal hearts, right? It's hard, it's going to be harder to do that when you have a really, variable morphology. So this was super challenging. We knew it was
Mhm.
super challenging when you went into it though, right? So, there
Not
you
as
go.
much, but especially if you're trying to train on such subtle differences in
Mm.
spatial morphologies,
Right,
you need the data to be everything else that need to be absolutely perfect,
right,
like completely aligned, completely
right,
Also,
conformed. So
not all patients have the same four features.
right.
Some of them
Okay.
like don't have the aorta like pushed over. Some of them
Yeah,
don't have hypertrophy.
exactly. It's highly, highly different. So, yeah. So sometimes AI doesn't matter.
yeah.
Right? Humans are better at this one
Mhm.
right now.
Yep,
Okay,
absolutely.
great. Thanks, guys. Let's move on.
Thank you.
Cassie, you ready? And everybody ready?
Yep.
Awesome. Thanks for your patience.
Oh yeah, no worries.
Thank
I
you.
like I like AI doesn't matter as the intro to our presentation.
Sometimes AI doesn't matter. There are things it still can't do.
Okay. So hi everyone, my name is Maggie with my partner Cassie. Our final project is to talk about generating synthetic calcium lesions in cardiac CT images. So why we care about coronary artery calcium? Because it's a major warning sign for serious heart disease. And calcium buildup in the walls of coronary artery has been linked to nearly 9 million deaths as of 2021. In fact, people with significant coronary artery calcium are 3.6 times more likely to die from cardiovascular causes. But here's a hopeful part. By studying these calcium lesions, their makeup, and how they're distributed, we can gain powerful insights. Because CAC is actually one of the most reliable non-invasive markers for predicting heart disease, even more so than any other traditional risk factors. So if we understand it better, we can help more people. So what makes this challenging? So first, the CAC score data is underrepresented. There just aren't many open source data sets available for training or research. And secondly, the information we do get from calcium score is often too vague. Like take a score of 475, for example. Like what does that really mean? A single number can tell us much about what the lesion look like, how big it is, or where it's located in a vessel. So our goal, number one, is to augment the data set by generating synthetic calcium lesions. This helps us overcome data scarcity and improve model robustness. And then we're gonna extract richer metrics from lesions. For example, reflect their shape, their distribution, and composition. For example, how does like score 100 lesion actually look like, and where does it from? How does it? Where does it from in the artery? So by bridging CAG and CCTA, our second goal is to learn how these lesions behave, not just how many there are. So to be more detailed, when generating calcium, we need to go beyond just the calcium score. So we need, first we need coronary CT angiography, also CCTA scan. This gives us the anatomical structure of the heart. For example, here's the left coronary artery, and over here is the right coronary artery. And second, we'll be using coronary artery calcium, also CAC, score image, this highlight where the calcium deposits are. So they guide us in understanding the lesion location and density. So with both types of scans in hand, we use a GAN-based model to synthesize realistic calcium lesion. So up next, Cassie will walk through how GANs are applied in our project to make this possible.
Okay, so generative adversarial networks, or GANs, have shown to have very exciting potential in medical imaging applications specifically. So broadly, a GAN is a deep learning technique that generates synthetic image data. One big application is synthetic data augmentation, where GANs are used to expand on small data sets by generating new realistic looking examples. So shown here are just some examples of simulated data in various medical imaging modalities and organs, where the real images are on the left, and then in the blue box are all synthetic images that were generated by a GAN. So this shows how exciting and relevant this technique is in the medical imaging world. Next slide, please. To get more into the background, a GAN is basically an architecture that's made up of two competing neural networks, the generator and the discriminator. Random noise is input into the generator, which learns to produce fake images. The fake images, along with real image data, are then input into the discriminator, which tries to identify which are real and which are fake. The discriminator's output then helps improve the generator by updating its weights, where those weights are adjusted until the generator can produce fake images that are so realistic that the discriminator can't tell if they're real or if they're fake. So for our project, we used a specific type of GAN known as a conditional or CGAN. So while classical GANs are fed only random noise, in CGANs, the model is fed with additional information or conditions. So in our case, the generator and discriminator are both fed with CCTA data and a calcium score. So the generator then outputs a fake calcium lesion that has been conditioned on score, and that is what is fed to the discriminator. The discriminator is also fed real CAC scan images with real calcium lesions. Those are conditioned on the CCTA and calcium score data. And then the discriminator then determines if those inputs are real or fake, and the process continues. So we chose this architecture for our project because it provides the model with important clinical and anatomical context that it needs in order to produce realistic lesions. It's important for us that the lesions appear in specific anatomically correct locations of the heart and also reflect the clinical calcium score, which makes the conditioned element key for our tasks specifically.
Yeah, so as Cassie mentioned, our GAN model takes CAC scan as input. So that's like compared to different patients to decide which is better suited for our model. So on the left, we have patient A. You can clearly see two distinct calcium spots in the left coronary artery, and these are easy to locate and isolate. So it will be perfect for training the model to learn what individual lesions look like. On the other hand, the right patient B, the calcium is heavily clustered in fields along the vessel walls. So it's much harder to separate any individual lesions, like making it less useful for teaching the model about lesion shape. So we choose patient A as a better candidate. And this also taught us something important, like for early stage model training. It's more helpful to work with mild to moderate cases where calcium lesions vary in size and are easier to interpret, rather than extremely sick patient with diffuse calcification. So after we choose a patient, our next goal was to find and isolate a calcium lesion in a non-contrast CAC scan to train our model. So to do that, we first use ImageJ to adjust the brightness and add some coloring, basically just help us visualize spot where the lesions are more easily. Then we apply a threshold of 130 Hz per unit. That's the standard cutoff for detecting calcification. So anything above 130 shows up as white, and everything below turns black. So this makes the calcium stand out really clearly for us. And then we also tweak the window level to center it around the calcium range. So we could really focus on those lesions and capture them accurately. And using this method, we analyzed scans from 4 patients in total and ended up with 88 lesion data points. So having this small but clean set of preprocessed lesions has been super useful as a reference when working with non-contrast scans throughout the rest of our project. So now that we have identified the lesions, the next step is to calculate the calcium score, also known as Atkinson score. So it's a standard method we use to quantify how much calcium is in the arteries. Here's a basic idea of the formula. So the score depends on 2 things, a weighting factor based on intensity in pounds per unit, and also the area of the lesion, basically just like the number of pixels in that around the lesions. So the weighting works like this. If the intensity is under 200 Hunts per unit, the weight is 1, and anything in between 200 and 300 will put a weight, will identify the weight as 2, and anything above 400 Hunts per unit, it will be weighted as 4. So higher density calcium gets a higher contribution to the total score. Then our final step before model training, we look at the shape of the lesion more closely. So to do that, we draw a line across each lesion and plot the intensity profile along that line. So when you see a peak in this plot, it means the calcium signal. So if the value goes negative, that means we're in a dark area, like no visible lesions there. So now here's what we notice. Most lesions in the data set have a very steep roll-off on either side. That tells us the calcium has a clear, sharp boundaries, which is good because it means the lesions are well-defined and easier to analyze. We also use this profile to check for symmetry, like the shape of the lesion. So we compare the left slope to the right slope of each lesion. So if they match, meaning the rise and fall are similar, so the lesion is likely symmetric. So on the plot, the x-axis is left slope and the y-axis is the right slope. So if the point falls right on the x equal to y line, the lesion has a balanced shape. But if a point fars from the line, like the red dots here, it means the lesion rises quickly and then rolls down more slowly. That suggests an asymmetric shape, which might mean it's irregular or has some distortion.
So once we've identified the calcium lesions using the method that Maggie just described, we then used a custom MATLAB script to build our lesion data set for the model itself. So based on the preprocessing done in ImageJ, the user first selects a slice with a clearly visible lesion. You're then prompted to manually draw a circular ROI around each individual lesion. We wanted to extract as much data as we could from the few patients that we had, so we circled those small individual lesions one at a time. The script then calculates the Atkinson score for that lesion and creates a subfolder labeled with the lesion score, where each folder includes the original Hounsfield unit image of the slice that was used, a binary mask of the ROI, a JSON file containing the calcium score, and metadata, which is extracted from the DICOM header. So we repeated this for all the individual lesions in our patient data set, generating our library of real calcium lesions for the model to use.
Yeah, now that we have preprocessed everything, we'll work with 3 key inputs, the CCTA scan, the CAC scan, and a zoom-in calcium lesion patch defined by the RI mask. So like Cassie said, we wrote a MATLAB script that takes both CCTA and CAC image, each at 512 by 512 resolution, and use the RI mask to find the center of the lesion. So from there, we extract a smaller 128 by 128 patch around the lesion. This zoom in patch lets us focus on just the RI itself, like cutting out the surrounding background, because it makes it much easier for the model to learn what the lesion look like without getting distracted by noise or unrelated anatomy. So essentially, we'll give the model a clean, more focused view so it can learn to generate lesion more effectively.
So those are all the inputs, and then in the actual model itself, we used architecture that's based on this structure from a different CGANS paper. So we have a UNet style generator with an autoencoder with an encoder decoder structure with skip connections. As we mentioned before, the generator takes in a two-channel input, so the CCTA and CACSIAN data, as well as a scalar value, which is the calcium score. And then that generator outputs a one-channel lesion prediction using a sigmoid activation. And then the discriminator, we have a convolutional network whose inputs we pretty much already discussed.
Yeah, so now with our data set of 88 lesions, we trained the model, and here are some of the generated calcium lesions. So it's really exciting to see that the model is starting to learn the structure from epoch 1 to 100, 200, and all the way to 500. So you can clearly recognize the chamber boundaries and the edges are sharp and well defined, which is a great sign. Even more exciting is that the model is also learning. Sorry. Um, yeah, so the model is also learning to recreate isolated calcium spots. And that is super promising because generating clean standalone lesions means we're getting closer to producing high quality synthetic data that could actually help expand our data set in a meaningful way. So just a note, like to help with visualization, we added color to the input scans because this gives us better contrast and makes the calcium easier to spot. However, our model output uses a sigmoid activation, so the generated results are still binary, just black and white. But it's something we want to improve later for more realistic intensity representation. Also, the result you just saw on the last slide come from our best performing model so far. But before getting there, we experiment with different loss function weightings.
Okay.
And initially, we use a log again loss function, again loss weighting, and a high dice loss weighting, because we wanted the model to really focus on the lesion structure. But as you can see, that version struggled to detect lesion edges properly. The boundaries are either so soft or completely missing. So to fine-tune the result, we adjusted loss weights. We increased the gain loss to encourage model to generate more realistic looking structure. And we keep the reconstruction loss constant to maintain similarity with the input. And lastly, we lowered the dice loss just slightly to avoid over constraining the shape. So these small change has some impact. So the generated lesion become cleaner, sharper, and much more medically interpretable.
Can I ask a question about that plot? So
Yeah,
on the generated lesion,
yeah,
what's the red? I see binary color, but I also see red.
So
yeah,
if you go back a slide even, you can see that like it starts off with just red. So
here.
like Maggie was saying, like we had this coloration just to improve the contrast so you could like better see the lesion and like the intensities that matter, like see the contrast there. So our input of the real data is red here. And then we were using like a sigmoid activation. So we want the output to be binary,
Okay.
but like in early stages of training, it's still like, it hasn't decided like where on that sigmoid curve it wants the pixels to land. And that's where you see all red. And then like you start to see less red, like more black and white. And then in the end, hopefully it's all black and white. But
I see. And so, so this one, like the in epoch 400 to 500, the top one, all the red's gone, and it's popped in two estimates of lesions there on the generated version. Is the
Mm,
Mhm.
binary mask, right, of two lesions there.
yeah.
Got it. And then that lesion's a big guy. Okay. And then why does it, I guess, so you're trying to generate a total binary image. And so why is the background, like say on the second one in the epoch 4 to 500, the second row. So there's stuff to the left, the big island of binary stuff to the left. Why is that one? Nobody
That
knows.
has been the biggest struggle because, like, it's clearly
I
we're
don't
so
know.
thrilled it's learning
Um,
structure. Like, you can see all that structure in there that's not the lesion. Like,
Yeah,
we're excited that it is structure that correlates to something that's in a real image, but like, it's not the calcium. So,
right. It's interesting.
yeah, that has been our biggest struggle is trying to teach it to only focus on the calcium, which you would think would be the easiest thing, but
Yeah.
it likes to pick up on all that other structure as
Okay.
well.
All right, cool.
yeah.
Yeah. I mean, that's the main result. Like, I was just going to talk briefly about some of these loss plots
Sure.
that we looked at. Basically, like Maggie was just showing, like we did experiment with different weights of various loss terms to help guide the model towards better results and to focus on the calcium and get rid of that other structure, the other structures that were showing up in the generated images.
Yeah.
GANs are really sensitive to the hyperparameters that we honestly just didn't have the time or GPU accessibility to really fine tune and empirically test completely. So
Yeah.
this is an example of the training plots over epochs, which generally look really terrible. The generator loss, super noisy, really large, which is indicating a lot of instability. And then the discriminator loss drops off completely, really quickly, which indicates that training is probably just collapsing.
Yeah.
And then we have these other loss terms that are components of the generator loss.
Yeah.
Um, and so, like, we acknowledge that we don't understand. We ended up adding a lot of loss terms into our generator loss to try to fine tune things like shape, location, intensity. Um, we probably added too many at once. It became a problem with too many confounding variables. Like, we didn't really understand how to adjust the weights, how they were all
Right.
interacting with the generator. But what's interesting is these plots, like the parameters that produce these plots, were also the parameters that produce the images that Maggie showed. So the best like output images that we
Yeah.
had.
Yeah.
So yeah, while these loss metrics are definitely discouraging, the qualitative output definitely improved. Like we saw significant improvement over epochs, and so we saw that our model was able to learn, and like we mentioned, it was learning structure. So we're
Yeah.
super excited about that, but it's not reflected in these quantitative metrics. So that's something that we just have to
Maybe it's just lack of numbers of examples. I don't know.
like number of like of
Meaning
our data set.
like the training size or the
Oh,
set,
right.
if, I don't
Like
know.
we need to go further out.
Yeah.
Yeah, that's fair. That's something we thought about. So anyway, that's basically as far as we got with results. If you would just want
Yeah.
to touch on future directions, Maggie.
Yeah, I can talk about like our future direction. So right now, with the limit of GPU, the model is not quite perfect and it's learning, but it can not like it can be performed better with higher epoch, like 1,000 plus something, and then to generate consistently realistic calcium lesions. But if we improve the model performance, here's what we are heading next. So we wanted to build a simple interactive app, like something clinicians or researchers could use without needing to run the code. The idea is just that the users input a desired calcium score and have the model generate lesion that match that score.
And
Um,
the
yeah,
left hand upload CAC here, that could be that's a non-contrast CAC scan. They can
yeah.
have an arbitrary number of lesions or no lesions in it.
We thought about that.
Um,
We thought about like, would it be better if you could just input a CCTA scan? Because presumably you wouldn't have a CAC scan if you're using a data, like if you're not imaging a
Right.
diseased person. Um, so yeah, something to fine tune. But I mean, our model works with the CAC scan, so it would be nice if you had a CAC scan. That
Yeah.
yeah, you could start with like
That's,
a some lesions, and then we could add, build onto it,
mm,
things
yeah.
like that.
yeah.
That's actually a different application would be having a CCTA in the left one, which actually has
Mm,
CAC in it, right?
Hmm.
And then you
mm,
say, what actually would the CAC scan look like if we took one?
Right.
Because
mm,
that one is expensive in terms of radiation dose, right? Because you do that at 120 keV, and so it's not a zero radiation dose thing. It's like 1 or 2 millisieverts.
Hmm. Hmm.
So
mm,
that's actually a very interesting application for this.
Mm.
Okay,
yeah.
So
cool.
Yeah.
anyway, that's
Yeah, that's our project.
That was a hard project.
we
So
really were optimistic and didn't think it should have been that hard, but
yeah.
yeah.
I don't know. I thought it was going to be really hard. Um, okay, well, that's great. The presentation was wonderful, and I think the direction you took the project was great. So
Thank you.
terrific.
Thank you.
Well done.
Yay.
Good. Well, thanks, guys. Was a good quarter. Have a great summer. All right. And if you need a project, I don't know if you're doing like masters that require some kind of project, but if you want data for a project, don't hesitate to ask. Okay, we can work
That's
something.
awesome.
Okay.
Thank you.
All right.
Thank
Awesome.
you.
Okay, thanks so much.
Okay. Bye bye.
Bye.
Bye.